Madam, sir told that he will be joining in 5 minutes.
Okay, thank you, sir.
Okay.
Morning all, Mr. R from Intel. Balaji, Padmanabhan.
Good morning, sir. Thanks for joining, sir.
You can hear me?
Yes, yes.
Okay, thank you.
Good morning, sir.
Good morning, good morning.
Good morning, everyone. Am I audible to all of you?
Good morning. Yeah, I can hear you.
Thank you, sir. So we are waiting for a few more participants to join the program. Thereafter, we will start.
Sure.
Okay.
Is this Viplab speaking?
Yeah, people, yes. Okay, Biplab.
Yes, sir.
Okay, great to talk to you, Viplab. Yeah, good morning.
Good morning, Gaurav sir. Sir, Director sir will be joining in another 5 minutes.
Okay,
So-
okay. Thank you. Thank you.
Thank you.
Professor Krishnamurti has joined. Hello,
Yes, sir.
Professor Krishnamurti. Very good morning. And very good morning to all the panelists here. I hope I'm to say I'm audible to all, and please allow us to, you can say, for 5 more minutes, and then we start the inauguration session. Hello, Srarji.
Yeah, okay. Thank you, sir.
Good morning, Gaurav sir. Good morning, Feroza and all. Okay, yeah, sure. We can wait. Yeah.
Yeah,
morning,
and Mr. Anil will be joining now or will be joining later?
No, he will be joining, yeah, around Padmanabhan 10, correct? We told?
Yes, yes, yeah, 10 to 11. Yeah, but I have blocked this calendar for this inauguration also.
Okay, fine.
Yeah.
I think I will message and request him to join early.
Yeah, great. Thank you.
Thank you, sir.
Welcome.
Good morning, Gaurav sir. Good morning, ICT team.
Yeah, good morning. Good morning, everyone.
Good morning, sir.
Anil, good morning, Anil. You're on mute, I think.
Yeah, hello, good morning, Mr. Anil. How are you? I am Gaurav Trivedi from IIT Guwahati. With me, I'm with Professor G. Krishnamurthy, who is Dean of Industry Interaction and Special Initiatives, is also here. Our Director, Professor T.G. Sitaram sir, is joining in a couple of moments now, and then we will start the inauguration.
Anil, we cannot hear you. I think you're on mute. Still not.
Viplav, from your
Firoza
right,
madam.
can you unmute?
Firoza madam, Vineet Savla sir has not received a link as a panelist.
Anil
So
sir is unmuted.
Anil, sir, still we cannot hear you, I think, Anil.
Sir, we will share the link again.
No, Anil. I can't hear you, at least.
Yes, we can't hear him. Yeah.
Okay, now can you hear?
Yes,
Yes,
I can hear you now. Good morning.
Yeah.
Okay.
Yes.
Yes.
Yeah. Good morning, Anil.
Good morning. Good morning. So let me. Okay, you can continue to hear, right?
Yes.
Yes.
So
Thank you.
now, if I have to present, then let's see. How is that?
So maybe I think once some inaugural speech are there from the IIT side,
Yeah.
and then they will enable us on the bottom of the side of this particular WebEx. You see the share button, which might be
Here
grayed
I
out
see.
presently.
Yeah.
Later
Yeah.
it will be enabled probably like you in
Got
that
it.
way.
Got it.
Yes,
Okay.
yeah.
Okay. Got it. Yeah.
And Anil, thanks for your time today.
Sure.
Yeah, Anilji, am I audible, sir, to you?
Yes, I can hear you.
Yeah, I think I was saying something, and at the time you were on mute. So with me, Professor Krishnamurthy is here. He's Dean IISI, and our director, sir, Professor T.G. Sitaram, is joining shortly, and in couple of more minutes, and then we will be starting the inauguration.
Very good. Thank you. Nice to meet you.
Same here.
Thanks for having me. Yeah.
Actually, I'm sitting actually in a little bit lower bandwidth today, so I'm just
Okay. Yeah. No worries. Yeah.
for the better bandwidth optimization.
Yeah.
Firoza ma'am, I think Vineet Savla sir has joined. Can you make him panelist?
Yes, sir. Sure, sir.
Let me
Viplav,
check,
please,
sir.
yeah. Sir, good morning, sir. Vineet Sahula, sir. Professor Vineet Sahula, sir, has also joined. Gaurav, sir.
Hello, Namaskar, Vineet sir. How are you?
Good morning. Namaskar. Badhiya, badhiya.
We are with us, Mr. Anil Sama from Intel. He's a VP in, you can say, the Intel division, one of the Intel division. I think this. I'm sorry, I forgot.
Data center and AI group.
Yeah, data center and AI.
Yes.
Okay.
Nice to meet you, sir.
Nice to meet you. Yeah, please. Good morning.
Good morning.
A data center and AI group, Anu sir is working, and we are having Mr. Israr Sheikh here with us, Mr. Padmavan from Intel, and so I think this is the entire Intel team. With Swati Singh is also from Intel is here. Dr. Sankita Singh from NIT Patna, Dr. Meena, and you, I think you are here. We are also having Professor Krishna Murthy. Chitrikant Sahu is also here. Professor Krishna Murthy is also here from IIT Guwahati. He is Dean of II and SI, and through under which actually our own entire initiative is actually running. So,
Yeah.
so sir, we start in a. Firoja, can you please call Amaya madam and please request, please see when director sir is joining.
Okay. Okay, sir. Ma'am, sir, actually, ma'am informed that sir is joining. Actually, he's traveling, so a little bit issue he's facing, so he will be joining by mobile. So sir is joining in another 1 or 2 minutes.
I know he is having meeting with our one of the with government of Assam today, which is scheduled. So I think he told me that he will be joining little in between. So Professor Krishnamurthy is here. So Professor Krishnamurthy, and with your permission, shall we start the inauguration session?
Yeah, maybe we can start. Maybe later on, maybe we'll request our director to give the inaugural address.
Yeah, sure. Thank you. So, so Firoja, please start the inauguration session, and I think directors will be joining in between.
Yeah, only one request, Professor Vedi. So maybe when director will come, maybe that time maybe we'll give him this slot priority basis because he has other commitment. That
Yeah.
We'll take it. Okay.
Yes, sir. This actually definitely, no, we honor that. Thank you.
Sure.
So,
Yeah. Thank you, sir.
Firoja,
Yeah.
please start. Okay.
Thank you, sir.
Very good morning to all. Greetings to all the esteemed dignitaries, speakers, and participants present today. I, Biplab Sharma from ICT Academy, IIT Guwahati, welcome you all to the first day of this online one-week faculty development program on designing with FPGAs Intel, organized by IIT Guwahati, NIT Patna, MNIT Jaipur, IIIT DM Jabalpur, and IIT Roorkee. We are fortunate to have with us Dr. Gaurav Trivedi, sir, the Chief Investigator of ICT Academy, IIT Guwahati, with us. I would like to request Dr. Gaurav Trivedi, sir, to please come forward.
Thank you. Thank you, Biplab. First of all, I welcome all the dignitaries, our director, sir, Professor T.G. Siddharam, sir, Mr. Anil Sama, VP from Intel in data science, this data center and AI division, and Mr. Israr Sheikh from Intel, Mr. Padmavan from Intel, Ms. Swati Singh from Intel, and all my colleagues from other institute, Professor Vineet Sahula, Professor Sangeeta Singh, Professor Meena Pachore, Professor Chitrakant Sahu, Professor Balaji Madina, and all other participants. A very good morning to you. It's a great pleasure to host this particular joint FDP with Intel. And this is precisely the second joint FDP in Intel in the joint succession after Intel signed one you can say collaboration MOU, research and R&D development you can say pact with IIT Guwahati to work on FPGA design related technologies. This is our pleasure that Intel has you can say shown a lot of interest in IIT Guwahati, even remotely in the northeastern side, and now in coming future we have already you can say drawn the roadmap what we have to achieve and how we have to achieve. So this course precisely in is one of the you can say milestone of a roadmap. We all know precisely this FPGAs are one of the critical component of electronic system design and manufacturing nowadays, and there is no even the complex system like the processors cannot be designed without you can say designing without validating the design using FPGAs. AI, which is precisely on the boom today, and one of the you can say one of the experts from Stanford, he has recently quoted that not even 2% of the AI has you can say work has been done in the area of AI. Specifically, FPGA playing the critical role here because of its reconfigurable platform. So this particular course, I believe that what is being offered by Intel uh, is really the need of the hour. And with the Intel technologies and the Intel platform, and using the Intel virtual you can form, this adds a new dimensions to this. So once again, I thank everybody, all the participants and the dignitaries to grace the occasion of this, and I thank everybody to you can say join this particular inauguration session, and I wish that and I hope really that participants will really enjoy this course, and during valedictory we will be able to see a lot of you can say cheer on the face of participants. So with this I wish everybody a very good luck, and thank you. And Viplab, please please proceed with the inaugural proceedings. Thank you.
Thank you, Gaurav sir. Now, I would like to request Dr. G. Krishnamurthy sir to address the participants. Before that, I would like to give a very brief description, brief introduction. The Dean of Industrial Interaction and Special Initiatives, Professor of Chemistry and Head of Central and Instrument Facility. He did his PhD from Indian Institute of Technology, Kanpur. He is also a postdoctoral research associate in the year 2003. In 2005, he did some projects on spectroscopic and structural characterization of H pigments and their use as real-time monitors of transmissible spongiform encephalopathies. Dr. Krishnamurthy sir.
Thank you. Thanks for it. Honorable Director, IIT Guwahati, Professor T.G. Ram, sir, and Mr. Anil Sama from Intel, and Professor Gaurav Trivedi and the whole Intel team, and also the the organizing team from IIT DM Jabalpur, NIT Patna, MNIT Jaipur, and IIT Roorkee. It's our pleasure that we are here assembled for the one of the course mainly for the faculty development program. IIT Guwahati recently, our office itself, Dean office itself is new. It was created after our director took the charge to concentrate more on the industrial interaction and other things, innovation, entrepreneurship, IPR. These are the things to give more focus of that and encourage those activities more. With that, we are doing a lot of that initiative we have taken under his leadership and guidance. So we have made reasonable success. Recently, our director was also talking about now we have to concentrate on the skill development program also. this is one of the things ICT Academy is doing good. So we want certainly more such initiatives. We want to have it to encourage the skill development and programs also, in addition to innovation and entrepreneurship and industrial connect what we are doing it. So I am also happy that okay, in Intel we want to have that industry connect with all our activities. So I was happy that Intel is also joining this faculty program, because now industry and academia has to work together. Not work that touch is needed from always. We have to have it. And Intel, we have Intel supported some of our program. I also request Intel to come in a bigger way. And we have a research park, IIT Guwahati Research Park, where we already have some of the industries are already there. We have 25 plus companies are already there. We are also in touch with Tata Steel. They are also shown interest to join our research, because discussion is going on with them. So I also request Intel also to be part of our research park. So the research park, then it will give maybe, because it's rightly says right now it's a society. It's going to convert as a Section 8 company. So then it will be very close for internal also taking a space in the research park and work together with IIT Guwahati and the problems interested to the Intel, and also the intellectual properties of the institute can be used. And our director will be maybe highlighting it, because in citation per faculty, okay, then we are the number 2 in the country, and we are 41 in the globe. That is so that so the research output of our faculty, not only output, the quality of the output of our faculty. So in that way, that we want to have more industrial connect with our faculties and students. So I will request Intel also to explore the possibility, and we'll also discuss in maybe in further to have Intel to be part of the research park. So because of the shortage of time, I will cut short my talk. So I welcome all the participants for this faculty development program. It's a really, as I mentioned, it's a really indeed a pleasure that industrial connect is also there. With this, I will welcome everyone for this faculty development program. Thank you.
Thank you, sir. Now, I would like to request our chief guest of this program, Professor Dr. T.G. Sitaram, sir.
Yeah. Namaste to everyone. Thank you very much. Very good morning to you all. Sri Ajay Sama, Anil Sama, Vice President and General Manager, Intel PSG, and all other colleagues of Intel PSG, and all my faculty colleagues, participants for this faculty development program on designing with FPGAs. Ladies and gentlemen, very good morning to all of you. ICT Academy, now headed by Professor Gaurav Trivedi as a PI, is continuously working very hard to organize faculty development program, and also very high-ended training skill development programs as well. So it's a welcome sign, and I'm also very happy to see many institutions have joined hands. That's a very collaborative work with the ICT Academy at IIT Guwahati. And I also congratulate all the partners like NIT Patna, MNIT Jaipur, IIT DM Jabalpur, and IIT Roorkee, along with Intel. This is going to be a very useful course. Friends, all of you know, this is FPGA is a very new, and many applications rely on the parallel execution of the identical operations. The ability to configure the FPGAs into hundreds of thousands of identical processing blocks is very, very key. And this is going to really have many emerging applications. I think it's a very high-ended, program where focuses on Intel FPGAs, ARM, Quartus, AI, NLA, and have to be, it's all part of the, industry orientation, and Intel has a major role to play in this. So as part of the Skill India initiative, this program has been designed, focused on the current requirement of the industry as well as new researchers in these areas. So I'm very happy to see a very large number of participation in this course, both from industry as well as academia, and also very interesting topics have been also covered by both the teams, which is very interesting. And also congratulate the organizers for making this happen. And they're also using the technology to reach out to a large number. That's very important. So I just wanted to say, at IIT Guwahati, we have started a School of Data Science and Artificial Intelligence. And we have already started the undergraduate program through JEE. It's almost 1 year now. And we are also running the data science program through, as a master's program already for last 3.5 years. So, and recently we have hired a large number of faculty in this area, both in the School of Data Science and Artificial Intelligence, and also in electrical and electronics engineering. So, when I say large, it's more than 10-15 people have actually joined in this area, which is a very large pool, because they'll also bring in large number of projects, as well as large number of PhD students are going to join them. So this is going to be an important area for IIT Guwahati. And in addition to that, we have actively involved during these last 2 years in creating a very truly multidisciplinary education. And we have started a School of Business, School of Health Science and Technology, and then School of Agro and Rural Technology, School of Data Science and Artificial Intelligence, School of Energy Science and Engineering. Even in the School of Energy Science and Engineering, we are starting an undergraduate BTech program in Energy Science and Engineering. And again, entry is through JEE. And the idea of School of Business is we wanted to actually provide the courses like business development, finance, marketing to all our 1,000 BTech and B-Design students at IIT Guwahati, an opportunity to have a minor in these areas of business development, marketing, finance, HR, so that if they want to pursue their own career in a startup or an entrepreneurial venture, this will be a very added value to them. So I hope many students will utilize this opportunity and work in a very high-tech areas, as well as, excel in the entrepreneurial, so that they will be a job givers than job seekers. So this FPGA technology is a very increased adoption, and I think it enters into every area, cutting across, all the disciplines. So it's very ideal for young people to have a training, because its topic is very new. And I thought this workshop, this FDP, they call Winter FDP, would add value to all the participants. So once again, I congratulate Professor Gaurav Trivedi and his team for making this event a very large and very successful one. And I wish them a great success. And I thank Intel for coming forward to work. And I can see, a large number of people from Intel have joined this program, which is a welcome sign. And this kind of industry academia interactions would go a long way. And we have at IIT Guwahati taken this as a very important step. We recently hired many of the industry people as professors of practice at IIT Guwahati and a part-time. And also a large number of international faculty has also been added to our list of faculty. And we are having a large number of collaborations as well. Okay, as Professor Krishnamurthy was highlighting, faculty have done very well in terms of their publications. In the QS ranking, World Ranking 2022, in citation per faculty, IIT Guwahati happens to be number 2 in the country after Indian Institute of Science, and number 41 in the world. So which is a very, very unique. And I looked at even this year's publication, they have done a very similar number as well. So anyway, we have, I mean, the ranking agencies are looking at it, but close to about 2,100 research publications have been published by our faculty, who are about 450 or so. Today, IIT Guwahati has close to about 7,500 students, and we have started a complete offline activity from this month. So, you know, the campus is now with a large number of students. Last 2 years, it was a very difficult time. So taking this cue, I would like to invite Intel and his team, and also many of the other participants, distinguished speakers who are there on this platform, to come to IIT Guwahati and see what our faculty and students are doing. It's a fantastic environment and also the place. So I invite on behalf of IIT Guwahati to all of you. I thank again the organizers for giving me this opportunity to share some of my thoughts today. I wish the program a great success. Thank you very much. Namaskar. Jai Hind.
Thank you, sir. It's me, Gaurav here. And I just want to add that without the motivation and the support provided by you, I have to say this couldn't have been happen. And I really thank you personally, as well as your colleague, as a junior as well, that without your support and motivation you provided us, we are able to do some work which is being appreciated now. So thanks a lot, sir. And thanks a lot for enlightening all of us. Thank you.
Thank you. Namaskar.
Thank you. Viplab, please go ahead.
Thank you, Director Sir, for giving us your valuable time and being a part of this program. Now, I would like to request Chief Investigator Sir from MNIT Jaipur, Professor Vinit Chawla Sir.
Saula, sir? Saula, sir, are you there?
Yeah, Gaurav, I am not panelist possibly, but I can speak possibly. Can you hear me now?
Yeah, yes, sir. Yes, sir. Yes,
Yeah.
sir.
Thank you for inviting me here, Professor Sitaram and Professor Krishnamurthy, Dean at IIT Guwahati, Mr. Anil Sama from Intel and his team, my colleagues from all other academies. I think I should congratulate IIT Guwahati, especially Gaurav and his team, for actually making efforts to organize such high-end and very supportive programs from industry side. I think this is a very good addition and very good for a cause of education from the industry side. Thanks to all experts from industry, Intel. I also heard and read somewhere that Intel FPGAs are now fortified with AI component, and that way they are much ahead of the other FPGAs, not even Xilinx also. So I think this is going to be a milestone in IoT design in some way, edge devices design. And I would like to listen to these talks here. This is 11th program in this season for winters. 3 more programs have to come, which are jointly organized. And I again congratulate Gaurav Trivedi for putting such an effort and inviting expert. And I congratulate all participants to be here, and thank you, Gaurav, and thank you other people. Thank you very much.
Thank you, sir. Thank you. And in fact, it was again, I will say that you being leading, I have to say, this entire our consortium is one of the pleasure working with you. Thank you, sir, for the motivation.
Thank you, Gaurav.
Thank you, Vinit Chawla Sir. Now, I would like to request Joint Program Coordinator of this program, Dr. Citrakan Sahu Sir, to address the participants. Citrakan Sir, over to you.
Yeah, very good morning to all the participants, and very good morning to all the dignitaries who joined the event in the inaugural session. I like to thank Dr. Gaurav Trivedi and Professor Vineet Sahula for giving me a chance to coordinate this event. So from MNIT Jaipur, around 75 participants has registered for this FDP program, and mostly are the faculty members from the various institutions across the country, because it is an online program, and many students from MNIT Jaipur are also participating. I especially called MTech VLSI student from MNIT Jaipur to participate in this kind of event, so that we'll get to know what are the industry is doing, and where their expectations, and they should learn about FPGA programmings. And especially thanks to our director, sir, MNIT Jaipur, who has given a trust that I can coordinate this event. Thank you very much, and thank you all the participants for joining the event.
Thank you, sir, for your nice words. The principal investigator of NIT Patna, Dr. Gaurav Gupta, sir, is in another program. So because of this, he is not joining us. So we have Dr. Sangeeta Singh, madam, from NIT Patna. Sangeeta, madam, I would like to invite you to the stage and please address the participants.
Thank you, sir. A very good morning to all of the participants, panelists, organizing team. I'm Dr. Sangeeta. On behalf of ICT Academy and IIT Patna, I would like to welcome all the participants registered here. I would like to welcome all the panelists, and especially Anil Sharma sir, the Vice President and GM of Data Center AI Group for Intel. And other speakers we have like Ishrat sir, Padmanabhan sir, Fpga, and Fpga, and Raghavendra Bhatt sir. And I would like to see forward to this course content, because I myself interested to learn a lot, and we the academicians don't get this chance to have a direct industrial exposure. So probably this next 40 hours or 5 days, we are going to have a very productive time ahead. And at the end, I would like to thank Gaurav Trivedi sir, ICT Academy team, IIT Guwahati entirely for organizing such useful interactive FDP. Let us have a productive time ahead. Thank you, everyone. And at the last, I would like to say thank you on behalf of Dr. Bharat sir and Dr. Veena Panchore ma'am, who is from my team from NIT Patna. Thank you, everyone.
Thank you, madam. The chief investigator of IIT Roorkee, Dr. Sanjeev Manas sir, is not able to join the program because of some technical difficulties. Now I would like to invite Professor V.K. Gupta sir, the Joint Program Coordinator from IIT DM Jabalpur. Over to you, sir.
Okay, thanks. And good morning to everyone, dignitaries and the participants. On behalf of the IIT DM Jabalpur ICT Academy, I welcome you. And it is one of its kind FDP, because most of the FDPs we are conducting, they are from the academia side and this is from the industry side. So I welcome all the participants and hope that the participants will be enjoying the sessions from the industry. Thank you very much.
Thank you, sir. Now I would like to request Mr. Isra Sheikh from Intel FPG. Isra sir?
Sure. Yeah. Thanks everyone, Professor Director IITs Guwahati, Dean sir, all the dignitaries from other college, Anil and Intel team. This is one of the event which we have and started earlier also, as Professor Gaurav was mentioning. And we see that, like, what we see that to have a collaboration and literally 1:n, how we can take up this to many more participants. And so that's one of the demonstration we have done it here. And also most of the people, those who are participating and the participating college, they have our board. that board, how to access virtually, that's another demonstration we have done. See, the boards or the system can be accessed virtually very much, but given the size of the board, and it is the starter board, few of the things, boards, and how we can take up those virtually, this is one of the innovation which we have done. I would like all the participants to take advantage of this particular course content which are coming. The people, our team from Intel, those who are coming here to deliver the series, they have done spend a good amount of time to prepare the session. Take advantage of that. Install the tool on your computer. Go online the way the sessions are going on. Run the tool. If you have access to the board, try to realize the program which you have getting through, and then see that, like, you know, you are taking most out of this particular program. So again, I would like to thank Professor Gaurav and managing team here for this particular event, and I would like to congratulate for this session. Thank you.
Thank you, sir. Now it is time to proceed towards the keynote session. It will be taken by Mr. Anil Sama, sir. He is currently the Vice President of Intel's Data Center and AI Group. He is General Manager for Programmable Solutions Group in India, responsible for developing FPGA, structured ASIC, and associated IPs. He is a seasoned leader of this global research and development team, covering silicon development, platform hardware, and software development. He has worked in Intel for the last 3 decades and has led several teams across CPUs and platform designs for PCs, servers, smartphones, tablets, wireless and optical networking. And now I would like to invite Mr. Anil Sama, sir, to this program.
Thank you. Thank you, Professor Sitaram, Professor Trivedi, Professor Krishnamurthy, and Professor Saula and others for setting the stage for this. Very happy to be here to give you an overview of what I see, what Intel sees as, you know, the future of our data centers and the technologies that the AI revolution is going to drive, and how FPGAs will be, you know, in the center of that whole movement, and how it's very relevant that we are here for this few hours of training session. So let me know. Can you see the screen that I'm sharing now?
Yes, sir.
You are able to see now, right? Okay. So my talk today is going to focus on just a minute. Yeah, so I've titled my talk as, you know, data center of the future, and how we can partner with academia and you know, collaborate for what I call the heterogeneous computing era. And what is that heterogeneous computing era, we'll understand as we go through this talk. But basically, in short, you can think of it as, what are some of the hardware and software trends we expect to see given this coming AI-driven workload explosion, right? And like it was mentioned earlier, we have only seen the touch the surface so far, right? Only about 2% of data has been mined. The AI field and AI-driven decision making is at a very nascent stage, and it's set to absolutely explode. So once it explodes, what does it mean, and how do we get ready for that? So that's really what I want to kind of emphasize through this talk. Now, before we get to you know, key data center trends and hardware and software trends, let's just take some historical context, right? So today, you can see that internet is available to, you know, pretty much majority of the globe, and even in India, about 50% of our population now has access, right? So they are participating, they are generating data, consuming data, and they are in a way contributing data, right? Which in an anonymous way, but this is all out there for that data to be mined, right? So more and more, as we use the internet, as more and more people connect, more and more data is being generated. Today, we are in what we call the cloud everything era, right? So everything is cloud-based. Think about it, whether you use a smartphone or a tablet or even a PC, today that PC serves as a client, but really a lot of the workloads are processed in the cloud, right? So it used to be that a decade ago, we used to have applications that we downloaded on our client and they ran locally, but today a lot of processing happens in the cloud. And we are basically served the results on our screens, right? So it's true digital democratization in a way, right? Because in a sense, everyone is starting to participate, everyone has a voice, everyone contributes data to the data economy in a way. So now this cloud everything era is also giving rise to many disruptive business models, okay? And I'll give you a couple examples here. So take, for example, a startup or a small or medium IT enterprise. Today, they don't have to set up their own IT infrastructure or compute farms or data center anymore. They can actually go rent that as a service from a hyperscaler or a cloud provider, right? So we call that a service, or infrastructure as a service, right? So you focus on your core competence, which is your technology, your startup. Don't worry about the IT and the, all of this can be rented on the cloud. So that's one example of a business model that's new. It didn't exist, let's say, 10 years ago. Okay. Another example you can think of is, this very talk or this conference we are having, right? This training we are having. We're all sitting in our homes or offices or wherever, and the application is serving up the content over the cloud to your client, which is pretty much just a consumption device, right? But a lot of the processing is done on the cloud. So this is today's state. Now, what can we expect in the next 10 years? And what I call that as the intelligent everything era. Today, we are just at the tip of the iceberg, just touching the surface of AI. But pretty soon, the next chapter, what we call new use cases and disruptive models will emerge based on AI informing human decision-making that will be disruptive. We can't even imagine today what kind of use cases will come. We will have connected devices that will be talking to each other and to the cloud. And digital technology will continue to become more and more pervasive and drive new business models powered by AI. And these new business models, if you think about it, what drives those business models? So whenever you have some AI inference happening, there is a workload at the back of it that runs on the cloud or at the edge, right? So these workloads are what operate on the data to inform, either in real time or non-real time, the decisions that the businesses will need. These workloads and the computation that will be required for running these workloads is going to explode. And compute demand itself will explode. We will enter an area of what's called zeta scale computing, right? Today we are more on the exascale, will soon be zeta scale. So how much data are we generating today? Let's just have a look at that also before we get to the key trends on hardware and software. And what does it mean for compute requirements, right? Do we need to rethink the architecture of the data center of today, which runs the cloud, versus what it will look like, a few years from now, and how it's already transforming? So just a brief look at some examples, right? How much data do we generate today? Average internet user, and there are so many billions of us, 1.5 gigabytes of traffic per day. An autonomous vehicle, now starting to come into place now, 4 terabytes of data per day. Connected airplanes, 5 terabytes of data per day. Smart factories, 1 petabyte of data per day. Cloud video provider, 750 petabytes of video data per day. All data that is ready to be mined and used for artificial intelligence inference and informing business decision-making, AI-driven decision-making. So in short, we are generating data at a faster rate than our ability to analyze, understand, transmit, secure, and reconstruct in real time. Real time is the key. So much data, how can you do all this in real time? Unless you have really high and fast-paced, deeply pipelined computation engines. Now think about it, securely storing and managing this data with the associated computation techniques that will be needed to manage the data itself is a huge challenge. So even data engineering, if you think of it, is going to become a field on its own. How do you manage and securely access all of this data? Along with this data problem, there's also going to be an immense demand for compute architecture to scale up exponentially. And all of this data, like I said, is ripe for mining, analytics, and AI training, either in the background or in real time. So let's look at some examples again of how this data will be mined to support some new usages and business models. These are just examples, right? And what we can think of today, like I said, there will be use cases, business models that we can't even envision today that will come. But the some that we can think about, right? Across all sectors of the economy, you can see they are listed here. But I'll give some examples, right? So, which could be close to home. Maybe you're already starting to see some of it, right? So, let's say personalization in consumer shopping experience, right? Based on continuously updated, user profiles, your tastes, your color tastes, your choice tastes. The system learns and basically makes it more efficient. Next time you go shopping, it's directly there in front of you what you're more likely to like. Better patient care from your doctor based on your symptoms and historical data that is available with the doctor, but assisted by artificial intelligence from the anonymized aggregated data of the entire human population. This will also come. We can easily think of automated driving, accident avoidance scenarios. You can think about search and rescue, right, based on sensors and cameras imaging in the field. Let's say some child is lost. Now you can deploy this whole system out there to basically do real-time inferencing to try and find some lost person. A use case which is very realistic, already starting to play out in some domains. So point of all these examples is what? That all of these compute workloads, there's a high diversity of these compute workloads behind all these disruptive and new use cases and business models that are sure to come. Now, when you break these workloads down, you realize that they need different computation engines. Some are single thread, they just want to run very fast. Some have a lot of data parallelism in 2 dimensions. Some have data parallel in 3 dimensions. Some are just very deep pipeline and deep parallelism, and ultra low latency is a need of the hour. Real-time inferencing is a need. So importantly, these different workloads will demand different types of hardware architectures in order to run on, right? So you take an AI business model, it's basically a software workload that needs to run on some hardware. And what we're saying is the hardware that each workload will run on will be different based on the nature of that workload, right? So far that's pretty intuitive. Now we call this heterogeneous architecture. At Intel, we also call it XPU, right? X can be anything, PU can be CPU, GPU, and AIPU, and in increasingly common FPGA-based accelerators. And that's one of the reasons that, one of the takeaways that I want you to have is that FPGAs are now seeing a different use, a new use, which is in acceleration of certain types of workloads that will become more and more important in the AI-driven economy. So what are some of these key trends in hardware and software that we can predict for the AI explosion? So I would make basically 3 statements, 3 key trends for this intelligent everything era. You can think of it as the next decade. One is that there will be a very large and explodingly large and diverse set of evolving workloads. Even the workloads themselves will evolve. They'll be diverse, they'll be very large, and they will continue to evolve. And they will need to run reliably on heterogeneous compute architectures, what we call XPU, deployed at scale. They need to be everywhere. They need to be in the edge, they need to be in the cloud, they need to be in the fog, wherever whatever as the use case demands. So by heterogeneous compute architecture, I meant CPUs, GPUs, specialized AI processors, FPGAs, right? And these FPGAs are a very interesting device for accelerator technologies. They often can be used for unique workloads that are best suited for deeply pipelined and low latency inline processing of applications that need frequent reconfigurability. Even the reconfigurability aspect of the FPGA is useful here, because as you train more data, you want to update your algorithm for better and smarter inferencing. So the reconfigurability aspect is also very, very important. And then lastly, the software programming challenge for all of these different workloads, all of these different architectures today, each has its own ecosystem, its own tool suite, its own debug method, its own expertise to be able to program to that. And we see that this is something that Intel is also driving to get ready for this next stage, adoption of one API programming model, which I will explain a little bit more in the coming slides. So let's explore these trends in a little bit more detail. So take the diverse workloads. I said the future is a diverse mix of CPU, GPU, AIPU, and FPGA accelerator, right? Why? Why all of these? Simply because these diverse workloads won't all perform well on any one hardware architecture. And you need it to be very efficient and run as efficient as possible, because the explosion will want to use all the hardware capacity out there all the time, 24/7. So some workloads we know require traditional general purpose computing on CPUs. We call them scalar, right? These are typically your databases or database accesses. Some workloads operate on simple vectorized data sets. They run more efficiently on dense GPUs. Some workloads are vectorized, use vectorized data sets, right? They run more like, for example, dynamic or weather modeling. Matrix data workloads run best on specialized AI processors. And this is primarily for deep learning training and for inferencing. And then we also have the spatial category, where ultra low latency and deep pipelining are required. So all of these different architectures are required in order to serve the explosion in diverse workloads that we are going to see. So what does this mean for the data center of the future, right? Today, if you look at data centers, they are pretty much CPU based, right? Some are GPUs, but let's understand how the futuristic data center will look like and how it will evolve to keep up with all of these demands. So think of the future data center as a massive computer, okay? And the traditional data center concept is that, a workload is assigned to a CPU, maybe under virtualization, and majority of the compute cycles that are run by that CPU, be it a Xeon or any other, is actually used to serve a lot of overhead tasks, like moving memory, encryption, decryption, compression, decompression, before the actual workload is run. So as a result, a small part of the CPU bandwidth available goes towards actual workload processing. A lot of it goes today into infrastructure processing. So the modern data center that we envision, actually, we see it moving to a concept of having at the network fabric a device called the Infrastructure Processing Unit, or IPU. Okay, and this IPU will handle and accelerate all our infrastructure functions. What I mentioned earlier, moving memory, encryption, decryption, compression, decompression, and these IPUs will then free up all of the XPUs to actually run workloads. So the data center owner will actually also be able to monetize the XPUs that they have in a better way, because all of it will be available to serve up real workloads, which is what the end customer pays for, not for the infrastructure part. Okay, so that's one thing you can see, that at the network fabric, you can see all these services, right, on the slide. Each service first has an infrastructure processing unit at the network fabric, and then they either have general purpose compute or storage computational services, or a collection of XPUs for acceleration. General purpose could be GPU, CPU, AIPU, and in some cases FPGA, and also AI services with a combination of general purpose and XPU, or GPU and AIPU. So this is the first trend. Data center is a computer, massive computer, evolving to be XPUs that run monetizable workloads behind infrastructure processing units. So that's the first trend. Second trend, if we look at it, is emerging use of FPGAs as an acceleration technology, or as an acceleration vehicle, especially where we need deep pipelining, low latency, and real-time inferencing. So many workloads today are already being implemented on FPGA. And the advantage of FPGA is that you can create custom compute pipelines, right? You don't have to use the compute pipeline that exists on a CPU or GPU that is provided by a vendor. You can create your own custom compute pipeline for on-the-fly, real-time use cases. And this can very efficiently be done on an FPGA. The compiler for an FPGA can automatically identify independent operations and execute them simultaneously in hardware, right? So they can program the FPGA in that fashion. And then when you combine this with deep pipelining based on your data set, you get real high performance and data parallelism in order to be able to do real-time inferencing in a very fast real-time way. So that's the advantage of FPGAs. And as you will see further, we are also introducing, easing the path to adopt these FPGAs by coming out with what we call as programmable acceleration cards. So Intel has introduced a family of FPGA-based programmable accelerator cards, looking at the trend that we see that these are going to increasingly be used in the data center. So they are basically a card that sits on a PCIe slot. You can put it into a server infrastructure behind an IPU, or sometimes even some of the IPUs are implemented with FPGAs. And you can implement any desired accelerator workload for the data center, for the edge, for the network, using these programmable acceleration cards. Some examples, right? So in the edge scenario, for example, here, a camera feed, right? A real-time camera feed at the end, you can do detection and recognition in real time using these FPGA accelerators. If you look at network infrastructure, a 5G radio access network today are seeing wide adoption and customer traction based on these FPGA accelerators at the edge and the network edge. In cloud, I already mentioned that IPUs themselves are being implemented in FPGA, but several proprietary acceleration technologies are also implemented on the FPGA itself. A good example of this is the Bing search engine that Microsoft has, is actually run and frequently updated and made better using Intel FPGA technology. So you probably feel it every day whenever you use Bing, but right behind that is actually an Intel FPGA running that acceleration. Okay, so that's the second trend. First trend, diverse and exploding set of workloads. Second trend, FPGA as a powerful acceleration technology. Third trend is there to address a challenge of software programming for all these diverse workloads. And this is where we have a very good opportunity to, build up the competence and the capacity in our ecosystem for this upcoming software programming challenge. So today, the very real challenge is that when it comes to the programming model for all of these different types of architectures, they each have their own ecosystem, right? They have their own language, they have their own tool suite, and their own expertise and training in order to be able to do it. And they, the challenge today is the separate programming models and tool chains. We are addressing that with what we call one API. So that is Intel solution to address this problem. So one API is a single programming model from all these multiple architectures and vendors, including FPGA. So what it does, one API abstracts away the XPU architecture details from the software developer via libraries. It delivers native code performance across these different XPUs, CPUs, GPUs, FPGAs, AI accelerators. And moreover, it is an open ecosystem, meaning that anyone can contribute to the standard. It's forward compatible. It's also vendor agnostic. So you could replace, an Intel GPU with an NVIDIA GPU, and it would still work. It also provides the XPU hardware infrastructure to the developer, the software developer, over our dev cloud to test and profile code for any software developer to test what they are developing. And we can see this one API approach, it really helps address the software scalability and portability problem, right? You learn once to write in data parallel C++, for example, and you can, based on the nature of the workload, you can target each of these different hardware architectures, and it would then basically seamlessly work. Now, I said one API also applies to FPGA programming and eases the workload development for low latency real-time accelerators using FPGA. Traditionally, FPGA is not a quote unquote easy technology to learn and apply, right? You need to know a lot of the low-level details about the RTL, how to write it, how to compile, how to make it more efficient, how to make it meet timing. Those fundamentals may still need to be learned, but the one API today also provides a path to compile and generate these custom compute pipelines directly from data parallel C++ code to an FPGA bitstream compilation. So it basically removes the need for developers to be intimately familiar and work on the actual FPGA programming aspects. And high-level synthesis from this data parallel C++ to FPGA bitstream. Bitstream is what actually gets programmed into the FPGA, is one area that's actually ripe for collaboration and academic partnership. So this is one thing we also would like to explore. So one API addresses the third challenge, the software challenge that we have for all of these multiple heterogeneous architectures. Intel has also developed an open FPGA stack to help ease this accelerator development further. So this open FPGA stack is an end-to-end open source infrastructure comprising of FPGA boards, commonly used IPs, and basic building blocks, which eases the integration into a platform environment. So when you take one API, you combine it with open FPGA stack, it really frees up the developer's energy and investment towards focusing on just the accelerator development code. And the intent also with this open source platform is that we can have community contributions on IP accelerators and other FPGA IPs. So it's kind of an open system. Okay, so what I have indicated so far is that to prepare for this coming AI workload revolution, the explosion that some we can predict, some we can't even predict, it'll be that big. is that there are significant opportunities for us for human capital development, for upskilling, and Intel is investing in these areas, right? We have the opportunity for curriculum development around one API, data parallel C++, open FPGA stack use. We're also looking to expand our existing FPGA university program, of which this is one session, right, happening in real time, with additional faculty training, dedicated lab hardware, and then also free FPGA system accessible over our dev cloud. So all of this we do to kind of make you familiar with our FPGA systems. This is currently in place with several tier 1 institutes, and we want to expand this further. We're also looking to create research internships, student placement pipelines into Intel with the requisite skill sets acquired via all of this course curriculum and training that we are undertaking. And we also have a strong startup incubation efforts, where with these, we are looking to incubate startups that have good accelerator ideas using our Intel India startup incubator that we have, where we offer consulting, we offer lab space, hardware, and marketing connects. So in short, Intel is very committed to accelerate innovation and to collaborate to build the skills for FPGA-based accelerators, which we believe is at a nascent stage today, but set to explode in use. So with that, let me just summarize. I hope 3 things you will remember about this, what I call intelligent everything era. Large set of diverse workloads that will need heterogeneous hardware and associated accelerators that increasingly are implemented on FPGAs for real-time inferencing purposes, and a unified programming model using one API. These are the elements that will underpin and define data center of the future. Secondly, it's a great collaboration opportunity for Intel and academia to upskill, to get ready for this coming explosion, and we are here and ready to partner on that. And this area is also ripe for startup activity, and we are ready to incubate promising ideas with help from Intel on technology aspects as well as marketing connects. So that brings me to the end of my talk. Hopefully it was somewhat enlightening, and I kind of painted a picture of where this is going in terms of hardware and software and how we can collaborate and get ready to meet the need of the future. So with that, I wish you a fruitful session of learning about FPGAs in the coming training sessions, and I will pause here and see if there's any questions I can take. I'm happy to answer.
Yeah, Professor Anil, actually, I have one question here from you. I'm Gaurav Trivedi.
Yes.
Actually, when you are talking about this Intel, this platform particularly, this data parallel C++, okay, this particular platform, I'm going to say because this is my group actually is here working with working on this this FPGA design really up to a very, you can say, very expert level itself, and that is one of the reason actually Intel and IIT Guwahati has collaborated, and as you might be knowing that Intel is coming up with an COE here at IIT Guwahati named FAME Labs. So FAME stands for the FPGA and Embedded System Design Labs here. So so here in this, when we talk about this data parallel C++, so I'm to say when we write, you can say high level program using let's say certain let's say if I talk about although this is let us I write a program in C, there's some C or C like, you can say program, I can say embedded C, something like this, and then I just synthesize, then the program doesn't give me the enough you can say optimal area and power. Okay, so because I'm to say the output depends on how the particular program is written. Okay, it's a person dependent, and the person's, you can say, capability of writing a program dependent. So what kind of I'm to say efficiency is very much I'm to say provided by this Intel data parallel C++ program paradigm as compared to other such platforms. That precisely, simply, I just want to know.
Yeah, so I think, like I said, we are still early in this stage, in this journey of one API and data parallel C++, especially to FPGA path. So yeah, and it's an area right for us to collaborate and actually set the direction. So yes, there are not all the answers today, but this is the direction we are driving in. And the basic infrastructure framework is there, but we need to improve on it and make it more efficient. So I actually hope that with the FAME lab which you have set up, we can actually partner to see what is the need and how do we improve it, right? And Intel and your teams can collaborate on this.
Yeah, in fact, I'm to say because I'm working closely with Mr. Shah Sheikh and Intel FPGA team, and I'm to say other from the you can say this team from the research part also are I'm to say there with us. So I will definitely explore in my research group this data parallel C++ platform in the one API, and I will definitely going to use it. So
we welcome that. Yes, thank you for that.
And in fact, in future, I will say that one program entirely on this complete this data parallel this design using the this one API platform we will host at IIT Guwahati, and I hope that this will be really beneficial to the users.
Wonderful. Yes, wonderful.
Thank you. I request there are a few questions in the chat box. There is one question from Mr. Adesh Kumar. In what sense Intel FPGA and are different than that of the Xilinx? This is a question from one of the participants.
Yeah, so basically Intel FPGAs and Xilinx FPGAs both address kind of similar need, right? I mean, it's if you look at the entire ecosystem of FPGAs, we are the two main players, right? And we both have similar kind of products, but if you look at our Agilex product line, which we are just launching, we believe we have a significant advantage on both power and performance. And this is starting to now bear fruit as we engage with many of our customers. So we believe that with some of the open FPGA stack and one API parts we are putting in for accelerator workloads as well for the data center and edge and network, we have an edge when it comes to meeting power and performance. Because even if you look at data centers today, power is the number one spend for a data center, right? And so to the extent that you can bring that down, your product is that much more competitive. We believe we are there, and we're also on a treadmill to continue to improve. So yeah, hope that answered the question.
Okay, one question from Mr. Arun Kumar Zala. It's a very trivial, I think. What is importance of FPGA?
Okay, so FPGA is a very wide applicability of usages, right? You can use them in embedded scenario to implement some hardware function and permanently leave it there. You can update it because it is field upgradable. So unlike a traditional ASIC or SoC or a CPU, where once you implement it, that's what it does for the rest of its life, right? FPGAs are field programmable. So once you can set a certain implementation, and then whenever you have the need to upgrade that implementation or maybe go to a completely different implementation, you can actually do that in the field. So in that sense, they're a different class of silicon device, a very useful and upgradable kind of device.
Okay, thank you. In fact, there is one more. Okay, there is a message actually. Okay, this is our collaborator. I'm to say my colleague from IIT Jaipur.
Thank you, Gaurav. I'm Vineet.
Okay, yeah, sir. This is Professor Chitkan Sahu is saying that please discuss brief guideline about Intel and academia collaboration. Okay. He just want to know a little bit more about it. So somebody from Intel can you can say somebody from Intel actually can answer this.
Yes, we have an Intel academic, a program that engages with several tier one universities, and if there is a maybe we should have a follow up with one of our leaders that leads this program, where we can come in and explain exactly how we engage and the kind of activities that we do. But in short, today, if you look at our FPGA development at least, and we have developments across the board on research in all of our platforms. But we have already engaged with almost 12 tier one institutes, right, on faculty development. And going forward, we want to increase that also to research and collaboration areas. So if you're interested to join this, I think the best follow-up will be that we have discussion with Sumit Verma, who's leading this from our side, and we can kind of give you an overview and how we engage.
Yeah. I hope, Professor Sahu, I think this answers the question. And if there is more, then I can definitely provide you some more information about the Intel Academia collaboration. In fact, actually, that work is still going on because Intel and IIT Guwahati is working to set up a nationwide platform for FPGA design, and but Anil has already said that this is one API. So I think. So like the Intel One platform, something like we are working on to develop on this. I think more information I will provide you in a short span of time. One more thing, Mr. Anil, I will add to the Intel FPGA. I think this will be very then this will really be very enthusiastic for Intel team to learn about it. This is my own experience. For a very short period of time, for 2 years, I was developing an FPGA-based solution for high-frequency trading in the share market.
Okay.
After 2008, in 2008, as you know that Government of India and the NSE allowed algorithmic trading and in National Stock Exchange. So I was working on that. I was working on one of the solution. In fact, our solution was deployed as well. For that particularly, we used when we figured it out. In fact, the speed is the you can say the speed is the as you is the key there. Okay.
Yes, as close to real time as you can get, it's better, right?
Yeah, so actually we used, I tested in fact 10 or 12 high-end FPGAs at my end, and finally I chose this Intel statistics I think for that particular purpose. It was giving us the best performance. This is my own feedback to, this is on my, you can say, like addition to this particular program.
Yeah, no, I like that example because it's very real and it says how you can use this custom compute pipeline aspect of the FPGA, deep, broad as well as deep parallelism to achieve very real time, very close to real time processing. So yeah, great example there. Thank you.
Yeah.
Any more questions from the participant side?
Yeah, may I?
Yeah, sure, sir. Please go ahead. Sorry.
I am Vineet Sahula from MNIT. Thank you, Gaurav. Mr. Sama, I think this is very enticing for us to learn about Intel because we all have been bombarded by Xilinx right from the beginning. And for last 1 year, I'm learning that Intel has already few things there which world is trying. The AI accelerators built in that way, which you explained that it is in data center and compute intensive. My curiosity is how much of it we can actually deploy to the edge devices or IoT part, because we need the energy efficiency there rather than much of the brute force compute. But we need the compute throughput there. But rather than that, the primary benchmark is the low energy efficient.
Yes, agree. So, I mean, clearly on the edge, when you have, battery powered devices and those kind of scenarios, then it's a trade-off. It's a trade-off. So, but you can still use it for FPGAs are very useful to create and develop some algorithm. And then when you want to deploy it in mass scale, let's say you want to, really proliferate some accelerator device which you have developed on an FPGA on the edge devices, we offer a path to go from FPGA to what we call structured ASIC, which is lower power, lower cost even, and also from structured ASIC to pure ASIC. Because once you develop a custom pipeline, you can take it to ASIC as well. So for broad deployment, that is a path that some customers are considering. So you start developing FPGA, tune it, get it right, deploy it in the field, get enough feedback, finalize your implementation, then you can go to ASIC. And that's also a very powerful path, actually.
Okay, so just request for one help if you can, like we are proposing now there is a call for chip to startup from MIT, Ministry of Electronics, which I think every IIT and NIT are attempting to participate.
Okay.
That program is an extension of special manpower development of VLSI program, which is running for last 20 years in all IIT and NITs. So we were proposing one on AI accelerator, energy efficient AI accelerators for IoT devices.
Okay.
If you can connect me to somebody in your organization where we can have some kind of, like it's a technology transfer level we have to describe to the ministry in our project. So if we get some help from you in like getting a collaborative learning for us, and possibly the outcome can be absorbed by you. So this is my just request to connect to
take for action to follow up on this, and Israr, myself, and
I've taken a note, Anil.
Sumit will follow up. Yes.
Okay, I will ask Gaurav for your email and connect it. Thank you very much.
Good.
Thank you.
Sure.
Sure, sir. I will definitely provide the email. Our ICT Academy, you can staff members are here. So Ms. Frojahak and Mr. Viplab, please send the email ID of Mr. Sama sir to Professor Vineet Saula sir.
Okay, sir.
Okay, sir.
Thank you.
And so I think so are there more questions? Oh, okay. Okay. There is one question from one of the participants. I think one more question I will take. This is the last question for this session. I have a question regarding this discussion that why would we choose FPGA over VLSI?
Yeah. Okay, so
I think she would like to ask why we should choose FPGA over the real silicon fabrication. I was setting through.
Yes, yeah.
Like
so I think FPGA is very powerful device when it comes to developing some new technology paradigm, practice it, tune it, because you can continue to update the implementation. See, with a VLSI device like a SoC or an ASIC, like I explained earlier, it is very expensive, right? To tape out an ASIC or a SoC these days on the advanced nodes, you're spending millions of dollars, okay? And you only get one chance to get it right? Now, let's say you implement that, and you want to then again fine-tune your implementation, your hardware implementation. You have to do another, what we call tape out, right, in VLSI. And that costs, again, millions of dollars. Whereas with FPGA, you have one device which you can program your implementation into, and later you can continue to erase that, reprogram it, right? So that is the beauty of FPGA. You have one hardware platform, one system, and you can continue to upgrade your accelerator or your implementation, your logic, okay? Now, the downside of, you might ask, okay, why don't we do this all the time? Why do we even bother with doing ASIC, right? The downside is that you have higher power with this approach. Now, if power is a major concern, then the path is, like I described in the earlier example, you can fine-tune the implementation using this FPGA and then go to structured ASIC or even ASIC, full VLSI ASIC, eventually. Spend the millions of dollars, but after you develop around FPGA. So that's kind of the evolution path of new technology development, especially when standards are continuing to evolve. You don't want to freeze your design. You want to keep up with the standards, or even set a standard, and you're kind of practicing new algorithms, new implementations. This is kind of a very efficient way to do it. So I hope I answered that question.
I think the participant psyche would have agreed to this. So I think this is very right and a very apt answer for this question. So I think I think there are no more questions here in the forum. So with the permission of Professor Vineet Saula and my other colleagues, I thank you. I'm to say, I really thank you for this inaugural talk. It was really nice, very elaborative, and in fact, this was one of the best talk actually I've ever attended in last couple of years. A lot of, you can say, pointers for me also. So thank you, Mr. Najib, for this.
Very happy to hear that. Happy to be here, and I'm looking forward to strong partnership with academia on moving this technology forward and building the skills that we need to capitalize on this future technology trend. Thank you for that.
Yeah, definitely.
I also join Gaurav in thanking you, Mr. Sama, and your team. Thank you.
Thank you. And in fact, Mr. Sama, this is you might be knowing that IIT Guwahati and Intel already has inked the MOU together, and both in the terms of the R&D, we are together. Okay, research and development. We are now identifying people and all. We have already reached up to the level 4 or 5. But the moment we start reaching, institute become more impatient and more. I'm going to say, so they want more. It's a stronger and stronger collaboration from Intel. And our honorable director has also invited you and other your team members to be here at IIT Guwahati. So once again, I just reiterate that invitation so that you
would love to
note
do
it
that,
out.
yes.
So
Yes.
as per your convenience, I'm just please visit our campus, and we are, although we are in the northeastern region, but IIT Guwahati is doing phenomenal work, as our director sir has also mentioned. And I think Inter-IIT Guwahati partnership will be in a different form itself, and will be, you can say, an example not only to the nation but to the rest of the world as well.
Very good, and I'm looking forward to visiting also. So,
thank you,
you
sir.
so much.
Thank you, and thank you,
Thank
Mr.
you.
Israr, for you can say, for your all the collaboration from Intel and all Paddy, Swati, and everybody is here from the Intel. I really thank you from IIT Guwahati really a lot, and from my colleagues also who have joined from MNIT Jaipur, NIT Patna, IIT Roorkee. Sanjeev couldn't join as he might be facing some issue, and IIT DIDM Jabalpur. I really thank all of you for this collaboration in this joint FDP program. And to participants, I really apologize because there might be some you can say glitches in you can say joining, and you can say rescheduling the program. But from our side, we tried to, you can say, pass this information at the best possible level to everybody. But if there is something you can say couldn't be passed correctly, I'm really sorry, and my sincere apologies for that. And I hope that rest of the program you will really enjoy, and we will meet the expectations. Thank you.
Thank you.
Thank you all. So on behalf of EE and ICT Academy, IIT Guwahati, we would like to thank all for joining us for the inaugural session and the keynote session. So with this, we are coming to the end of the keynote session. We will start with the day one, first day session. So there are a few important announcements for all the participants. We all request you to please note that from today onwards, all the participants are requested to join the session by their registered email IDs, because the attendance will be marked against the registered email IDs. The questions are to be put in the Q&A section. And if you have any query, then you can raise your hand. Mr. Viplab Sharma will always be there with you. He will unmute you, and you can ask your question directly to the expert. After the completing the session, you may raise your queries. So these are the two important announcements. Please make sure that you are joining the session with your registered email ID. Regarding the quiz, the quizzes are already fixed and the time slots are available in the schedule. You kindly go through the schedule, and all are requested to please join the quiz as per the scheduled time. There will be no repeat test conducted, so please make yourself available for the quizzes. Thank you. So I may request Mr. Viplab Sharma to please start with the day one first session. Thank you.
Thank you, Firuza ma'am. Now the first session is on introduction to Intel FPGAs. It will be taken by Mr. Israr Sheikh sir. Before that, we would like to share his brief profile with you. Mr. Isra Sheikh is the Intel SG Field Application Engineer Manager for India, ASEAN, and ANS region, supporting FPGA products. Isra led the customer support, enabled, and co-architect the innovation products that target emerging FPGA usage models across embedded, telecom, network, compute, custom designs. FPGA-based hardware accelerators, heterogeneous co-processing, edge, and AI are the recent customer-enabled programs which he is managing. He is also participated in Intel India Site Technology Office innovation programs, startup ecosystem enabled academia and research for FPGA and system design. Israr is frequent speaker and Intel and industry expert. Israr sir has over 20 years of experience in FPGA-based design, RTL, and validations. He holds bachelor's degree in electronics and communication engineering from Amravati University and PGDBA from Symbiosis, Pune. Mr. Isra sir, welcome to this session. I am making with a presenter now.
Sure. Thank you.
Over to you,
Anil,
sir.
thanks for your time, and really it was a wonderful, deep, exciting talk from you. Thanks. Okay, let me share my screen. Please confirm once you see my presentation.
Sure, sir.
Sure, sir. To save the bandwidth, I'm not coming on video. So let me start. So already, like, for me, stage has been set by Anil, what the use case is and what way the FPGAs are useful, what scenarios are there, why FPGAs are important, these things are there. So I will not go in deep on that, but I'll say that, like, what's the portfolio, what we have from the Intel FPGA offerings to the designer, to the universities, to the researchers, and what we have an Intel University program that I will be focusing here. So I'll start with the introduction to the FPGA. Those who are new here and wanted to learn more about the FPGA, I will try to briefly explain what is FPGA, and so that those who are aware, that will be refresher for this. I'll go over the portfolio, what we have, what options are there for us to choose. As Anil mentioned that, like, we have the new FPGA series, which we are sampling now and shipping to the customer, which is Agilex from Intel's 10 nanometer technology, and which is basically, like, majorly on the data centric and managing the data for processing, for in and out. That probably, like, I'll be explaining more. And then I'll be touching base, like, what other families, which is basically, like, earlier our family from the Agilex perspective, that is a static 10, mid ranges are area 10, and low end, and, like, the embedded applications, Cyclone 10 and Max 10, that details I will explain. Apart from that, I will be touching based on the software Cortex ecosystem, what board accelerations are there, what we have, and what university program and where the training references are there. Let's jump into the FPGA. A lot of people must have been aware, but let me refresh what this acronym is for and what FPGA stands for. So FPGA stands for, like, programmable, field programmable gate array. And like, the gate, when we understand, like, the field programmable, what it means is that, like, the hardware, the program, the system which is deployed in the field, still you able to reconfigure it. It's still you able to change the content, either the software, either the hardware, or some kind of, like, functionality is called as a reprogrammability. But what is basically the gate? We all know, we are electronics, computer, IT engineers. We all knows about, like, the silicon. Silicon is made up of the gate, small transistors. These particular transistors this is a very tiny, precise, and the way we see that technology, like, the 10 nanometer, 7 nanometer, and 3 or so smaller nanometer is basically, like, the gate size of these particular transistors. And that is basically, like, are the small chip which is basically make up this particular design, and that is referred here as a gate. And the array means, like, many mores, and they're manufactured on the chip. It can be the billions of transistors. When I say that, like, 2.7 million logic element, that particular logic element, like, has a good amount of, like, gates are available. And that particular gate maybe like 10 to 12 if you take for logic element to multiply, then probably like you can take huge amount of like in the gate this particular device density, if you say that, like and this field programmable, as I told you, like and exactly if you go a little bit on the deeper side, like it means the connection between the internal components and program after deploying it, like and that still programmables are there. So FPGA means, in other words, like the programmable hardware which are available to us, to the designer, to the researcher, to the faculty members, like how we can take the advantage still to upgrade it, realize new idea, new standards which are coming in, the changes which are required, kind of like seed sources which you want to get deployed and keep it upgraded one, everything you can do when your system is still there deployed into the field.
You're not able to see your presentation.
You can't hear me?
Yeah, I can hear you, but we couldn't see your presentation.
Oh, I'm sorry. Now you can see it, Padmanabhan?
Yes, it's loading now. Yeah. Thank you.
Yeah. Sorry about that. I think I missed out to click one more button. One second, I'm changing the display. Now you can see it?
Yes.
Thank you. Yeah.
Yes,
So I was there in this particular slide. I was explaining like what is the FPGA and what is the programmable aspects and why it makes field programmable gate alley. Because of the FPGA, you can take up that like programmable hardware, and you can program whether they're in your lab as well as when they're deployed into the field. So now let's go a little bit like how an FPGA become what you want to be it, like and this is basically like is made up of very small building blocks of the logic and other functionality, which can be memory, which can be DSP block. Let's see that like how it plays very important role and how it goes, like these are the basically like different building blocks are there. I choose based on my need. It get configured based on my requirement. It can get connected based on the functionality which is required, and those all functionality comes the way I as a designer write RTL code or write on abstract level, can be the C, C++ or DPC++, which has been spoken in the earlier session, and how it can take up to the configuration, like and how it will get connected, and to determine what functionality FPGA is performing from real world of the IOs to internal taking to various blocks, and then again data might be processing into various blocks, including the ARM core processor or any other control logic, and then going out the results to the next level blocks which are available. So how the block used here and what you have coded will get realized, like for example, like if you take like custom state machine or like 64-bit like a bit shuffle encoder decoder state machine control logic data path data manipulation data storage data processing, whatever is there, like if I'm writing a code, a major block which is basically like a lookup tables and a registers. This particular lookup table, if you see that like that it has like 4 input 5 input 6 input, it is a reconfigurable refactorable, and it takes that particular into a state based on the input which is coming, based on the functions which is coming, based on the earlier function which is getting transferred to this particular functions, like this is the one of the block. Multiple blocks get combined with other block which I'll be speaking in next few slides, and that will realize your custom logic block which you have coded again into the RTL or any of the abstract level. Other one is that like on chip RAM blocks, and wherever like you have to store the data, whether it's the small memories or bigger memories, for example like Ethernet frame, smaller frame or bigger frame, you want to store it into the inside the memory, these memories are also available. There are external memories also there. I will speak about that also, but these are the memory block which are like typically of the size of 20 KB, and that's blocks will get utilized here to realize silicon in function memory, which is required to realize your component or the functions which is there. So that's, we can see that small chunk or large chunks of memory in a green color on the right hand side. And that's, now let's take that realize. Now next block is that, like, I to do a lot of, like, maths, custom maths, DSP functions. So these are the DSP blocks which are available. I will be speaking more in the detail subsequent slides. What are this particular block? What kind of configurations are there? How it takes the coefficient bank? What way, like, first level, earlier level inputs will get combined with the next level of the output, and all this will be speaking. Now, if you see that, like, a dark green, blue color block, those are, we will be taking as a DSP functions. Now it's a time where, like, I have a custom functions, which is basically state machine order control logic. I have the memories which are required. I have a DSP functions or the match functions which has been realized. Now it's a time to get connected together. Now it's, see, from the input to the output, the data moving from various blocks, which is the control logic or the state machine, then to the DSP, to the memories, and then it is going to the next level or to the output. And when you do it, is all connected together, this realization is basically like, your blocks are connected with the custom routing determined by your code. And this is basically nothing but the FPGA, which is again defined as, like, full programmable gate array, which is basically a programmable hardware available to you. So this is, in short, I wanted to explain and give you refresher, those who are aware about the FPGA and those who doesn't know what is this FPGA and how we can use this to repurpose, reprogram within our lab, and when if it is deployed to the scenario. So as there are certain questions were also that, like, the FPGAs, whether to the data center, to the networking kind of environment, to the accelerator environment, or the FPGAs towards the embedded system, or the system which is starting from, like, board management controller, or to the machine vision or embedded vision robotics application, infotainment application. These are the FPGAs. Max 10 and the Cyclo 10 FPGAs has been used, which is we called as the lower density, low range of the FPGAs. If you see that, mid range of the FPGA, which is basically Area 10 and new families we are in making, probably by this year end, we will be announcing those new families, which is coming from the Intel latest fab, 7 nanometer, that will come also into the picture here. Now, presently, we are catering with Area 10 devices, which is predominantly used for the data-centric networking, military defense, and ADAS application. Now, moving towards the right-hand side, which is basically a two major FPGAs, which I am highlighting here, Agilex and Statix 10. Agilex is
slides,
big.
Sir, yeah, sorry, sir. The slides are not still changing. We couldn't see that.
There is a lag, but I have already changed it.
Yeah, we are still able to see only slide number 5.
At our end also, sir, slide number 5 is visible.
Okay, let me stop and reshare it. You can see my screen now? Hello?
Sir, it is
Yes.
freeze at our end.
Yeah, right.
Let me stop sharing and then again.
Yeah, sir, you can reshare, we can
it.
see, sir. Yes. Yeah.
Yeah, sure. Yeah. Sorry about that, not sure why. I will just share one application only. Paddy, you can see my screen, which
Yeah, yes, yeah, now it is in the right slide. Yes, thank you.
okay. And let me go in presentation mode. If it is not refreshing properly, maybe, like, then please notify me.
Sure, sure.
Yeah, you can see it?
Yes, yes, yes.
Can you reconfirm me that, like, I have moved to the next slide?
Yes, the slides are changing now. Yes.
Oh, thank you very much. Thank you very much. Okay. So I was here in this particular slide where I was briefing about the portfolios which are available from Intel for the FPGA product perspective, starting from, like, the Max 10, Cyclone 10, which is our lower end FPGA, which are required for the board management, machine vision, robotics, and infotainment application. Probably, like, Max 10 is the FPGA where still you can do the edge analytics. At the edge, it can be deployed because it takes very less power. Some of the battery and handheld devices uses this particular FPGAs. then comes to the mid-range, and then I was on to the higher-end FPGAs, which are the Agilex and Statix 10. So yeah, the functionality wise, if you see that, these are the targeted for the similar application. But if you see this particular FPGA, Intel Statix 10 is Intel 14 nanometer FinFET technology, whereas Agilex is from the 10 nanometer FinFET technology. Our Hyperflex architecture, which I'll be speaking in next 2 slides, has been enhanced from Statix 10 to Agilex to give you higher performance. And once you freeze your design, you feel that you have to go to the higher mass production. You wanted to have lesser on the power. EASIC is the path. We can directly migrate from this FPGA to the chip replacement, pin replacement device, which will be coming to you as a EASIC, which is a structured ASIC. So this I have spoken, more summarizing about the FPGA, starting from Cyclone 10, Max 10, Cyclone 5, Cyclone 10 again, which is the GX, Area 10, Agilex N, and Statix 10 FPGAs. Let me go details of each of this particular family. I will be starting from the Agilex FPGA, which is for the data-centric world, what we called as it is a very high performance for the compute applications. These FPGAs are there available. As I was telling that, this is a 10 nanometer process technology, which has innovation has come to this FPGA, and it has a memory coherent attached interface for the processor, which is coming next generation processor, which is there. Some of the samples are available for the customer, and it has a massive bandwidth. What is this? I'll be speaking again. And interconnecting, we have taken a tile-based approach, whether the memory, various analog, A to D converters, SerDes, or some of the logic functions which are coming from off any node, or any other suppliers or the IP, which can be integrated by means of EMIB technology, and that's basically any to any integration, and truly 2.5D, and next generation is 3D integration. System in packaging technology, the demonstration is this. And what advantage bandwidth perspective, lesser power perspective, integrating various technology perspective. This is one of the best demonstration in the FPGA families are there. Cortex and the softwares are the tool which are on the right hand side, or for the developer. Anil has spoken about one API. This is also the for the developer, those who are wanted to take their abstract level languages, C++ and DPC++, and realize to the XPU environment, and FPGA being one among them. So that ecosystems are there available for whether the bare metal you want to do the RTL, or you want to do on the abstract level, it is available to you. So this is the architecture of the FPGA which are available, and this is the second generation. As I was speaking from the Hyperflex perspective, is Statix 10 is the first generation, and Agilex is the second generation. And we have tuned our Hyperflex architecture. Hyperflex architecture is basically on the router element, we have more flexible. It carries flops also, so that you don't have to rely on the various flops which are available on the ALM logic, but the flops can be used for various retiming, repurposing, balancing the load purposes. It can be used. It has up to the high performance of 40%, whereas the lesser of the power 40% it consumes. If you see that 40 teraflops of the DSP performance, this is one of the huge and significant milestone which we have enabled for the customer to do their algorithmic, whether the communication, DSP, any kind of a high performance compute, maths applications. Here it can get realized, storage perspective, DDR2, 3, 4, DDR5 is also now enabled. HBM memory, high bandwidth memory, which is basically showing on the right hand side top. That's stack has been enabled here, and then Optane memory. Basically, these are the persistent memories which are in between of the DDR and the storage device. That particular memories are also available. SerDes technologies are the technology which is used for moving your data from one place to another, integrating the high-speed data, and Intel Agilex FPGAs are enabled for that. And 116 Gbps single lane transceiver data transfer is enabled into this particular FPGA. And as I spoke earlier, cache coherence connectivity with the PCI Gen 5 or CXL interface is one of the innovative features which has been brought into this FPGA and customer can use for their innovation. It comes in three major series. We call it F series, I series, and M series. F is stands for the wide range of application where SerDes goes from 1 gig to 58 Gbps. PCI Gen 2, 3, 4, and 5 will be also available here for the customer from the connectivity perspective. 1 second. Sorry, I have a power glitch and that's the reason. And then DDR4 can be attached with this FPGA for the data storage, whereas it has a quad-core A53 SoC processor also available here. And the major series carries this, except few of our series which are used for the evaluation purpose and some of the ASIC validation purposes. Like remaining that all the series which are available has the quad-core A53 processor. I series is basically the high performance processor interface and the bandwidth intensive application is been targeted for using the I series. SerDes goes to 16 gig of speed. PCIe along with the Gen 3, 4 PCIe Gen 5 is also been added into this. DDI4 has been added. Apart from that, processor interface, the options are all carried here. And then if you see that, coherent attach for the Intel Xeon scalable processor options are also available, which is basically a CXL. Adding to that, HBM memory options which are available, and that particular series is called as the M series of the FPGAs, which are on the right-hand side. So now coming to reusability, for the IP perspective, as Anil was mentioning in his keynote speak that this has been expanded, the FPGA offering. If someone want to take to the mass production and then still they want to use the IPs and the logic which has been utilized, direct replacement chip which are available by means of our eASIC technology, which is very much optimized for the time to market, high performance, and the cost benefit also customer will go. And someone want to go to the traditional custom ASIC flow, those are also available here. So IP reuse here, very flexibility, agile, optimized across the product life cycle is the offering to the customer. And so that no one has to worry on that. If I'm realizing today on the FPGA, using the FPGAs, can I move or not to move to the next generation mass production technology? That question has been addressed here. Little bit detail if I go to the tile-based approach, which I was speaking that these are the tiles which are there for the Agilex FPGAs which are available. Major tiles which you see that FPGA family, if someone is looking towards the more detail of that, which to choose, you will see that H, E, and F, E and F tile majorly. H is coming from your earlier generation. For the comparison purpose, how power wise we are doing, that has been used here. So E-tile devices, SerDes goes to 58 PAM4, 58 gig PAM4, whereas NRZ mode, it can go to 28.9. There are a lot of hardened IPs are available, whereas the F-tile, SerDes performance goes higher to 116 gig, whereas other features which are there on the E-tile will get continue here also. NRZ, if you see that performance has got to 32 gig, and then hardened IPs which are available has been extended here. Now you see the power perspective, as compared to our earlier generation H-tile, this is 40% less into the power, and these slides were made earlier when we were in engineering, it was getting fab the device, but now you see devices are available. We have seen far improved performance, some of the use cases where for minimum, like, we are seeing 40% improvement here. P tile and R tile, these are the tile basically like, the PCI Gen 4 and PCI Gen 5, which enables us connectivity for various other technology, which has been mentioned, which is required for high-speed connectivity, including VertIO, SRIOV. CXL is in PCI Gen 4, it has been enabled, and enhancement of VertIO and SRIOV, where the pipe interface and all has been enabled here. So get to the connectivity side, we are the leader here. 116 gig per second, single lane connectivity, PCI Gen 4. There is a high bandwidth for any kind of application, which include like 400 gig networks, network switches, edge application, edge analytics, data center workload, various which has been spoken in earlier keynote. This is the vehicle one has to look for. This is the one of the example with CXL I want to emphasize and highlight here. This is the only FPGA which has the CXL interface, which enables your FPGA to connect with the processor, and through the processor domain, you can see workload, whether it is getting realized to the FPGA or hetero connectivity, which you are using, so that workload has been partially executed on the processor domain and partially it is executed in a FPGA domain, which is other than the processor domain, and still combine your results or the outcome is been fed out to the next stage or to the user. That's basically like the beauty of CXL interface is there. In other words, you say that processor allowed other devices to get attached and get it used in a single domain from the single software flow, and user will not have a differentiation to see that whether it is attached to the devices or it is attached to the some of the restricted technologies interfaces. And would like to share here little details of the A53 quad-core processor which are available, which is basically 1.14 gigahertz processor are available from ARM, and it has a various interfacing devices are there, and you can look into the detail. But important thing is that communication infrastructure, enterprise data center, if someone want to use this and still want to go for a very compact kind of platform, this is the processor you should look for and utilize, which are hardenedly available, already available with the processor side. You don't have to shell out any logic element extra to get it realized here. DSP block, we have been traditionally supporting our DSP block from 18 cross 18, starting from to a huge combination of starting from 9 cross 9, 18 cross 19, and the cascading mode is also there, which can go this DSP over 64 cross 64. If you see that some of the data representation, which is basically B float, FP16 are the operators representation has been also enabled. Some of the participants were pointing that this has FPGA has enabled with good representation, which is required for the AI workload. These are the few of there. There are certain more things which are there, which makes this FPGA more popular. How your workload, your algorithm optimally get you implemented to get you the best performance, how it is attached to the processor. These are the another thing which is required when you are looking for hetero computing or any kind of critical workload to work in a processor domain also, or the XPU domain. This is the one of the best FPGA which are available to you. So this is the AI capabilities and applications which you see that representation are there. FP32, we have FP16 also, int 8 through int 4, and int 2 is also available. B float 16 options are available. This makes FPGA more power performance, give you the performance on the lesser power up to 40 teraflops of 16 FP performances. And if you go to the int 8, you will see that 92 tops of the performance available here. available from the FPGA perspective. Like, these are the memories which are attached here. You see their top blue color, light blue color. These are the on-chip memories, which is basically MLOP, block RAMs, ESRAMs are also available, which is equivalent of like, QSFP quad memories, QDR memories is basically equivalent is the ESRAM. In package, what we have, and I was pointing to you people like, HBM2, whereas the external memory, DDR4, 5 are available, QDR, RLD RAMs are available, whereas the Intel Optane persistent memories are also can be attached, starting from our static extend, now extended to Agilex with enhanced memory options are available for the external and the in silicon memory which are available. Security aspects is one of the important key aspects, features to continue to keep enhanced for the customer. Everyone is worried about the security, whether the data security, algorithmic security, system security, or the access to the system by secure manner when it is remotely configuring or when it is deployed into the field. This plays very important role. Like, SDM, like, secure device manager is being deployed, and various options are here available. Some of the important features which we have enhanced from earlier generation to this generation is basically like, private key, root of trust on the FPGA, public key only for the FPGA, an external root of trust if you are doing physically unclonable function, which is called as a PUF, widely used based keys, how to enable trust zone technology enabling. These are the important features and which has been enabled, implemented, and are available for the customer. Apart from the earlier one, like, encryption, authentication, tamper sensors, other technologies will continue to serve in this particular devices. So other thing is that I was highlighting that, like, second generation hyperflex architecture. I'll explain in next slide what is hyperflex architecture. Basically, what it does is that you faster your RAM, faster your routing, faster your clocking. And if you see that, like, from our earlier generation or conventional FPGA, it's still our competition FPGAs, Agilex FPGAs are there, and conventional routing. This has not been adopted as a hyperflex architecture. Still, Intel FPGAs are the first FPGA. You see that, like, hyperflex architecture, where the flops are there into the routing element. Also, are the FPGA which we are serving to the customer from static extend, and now Agilex is next generation. You see that, like, how total delay has been reduced from left hand side to the right hand side. And that's the power of, like, this gives us, enable us to run the FPGA on the higher performance. Like, I can run over 600 megahertz to some of the workload within the Agilex family. That's basically already proven and customer are using here. Those are the kind of, like, networking switches kind of applications here. You can see it. This is basically like, hyperflex architecture. What is that you are seeing? All these are the interconnect elements, like, the routing element. If you see the highlighted blocks are there, those are all the hyperflex register. It's ample of registers are available. Earlier, I have to, or still, if you are using the competition FPGA, you have to rely on the flops which are available on the LAMP or CLBs, all the slices, like, if you rely, whether you do the retiming, pipelining, or optimizing your critical path, you have to rely on the flops. I am giving you, Intel FPGAs are giving you the flexibility to use the flops which are available on the routing element, so that your pipelining, register balancing, retiming, and breaking your critical path, taking the frequency to the next level is the architecture and innovation, and the novel architectures are available for the customers to use it in this, like, Let's move to the other generation of FPGAs, which is basically static extend FPGA, which are still the leading vehicle for our customer to design high performance compute and their devices, their systems, which start from, like, GX, SX, TX, and MX family. recently in last year or so, we have added DX and NX family. NX is specifically built for one of the customer where, like, you know, the DSP has been very much optimized for AI and machine learning workload. TensorFlow has been added here. Apart from that, it has been enabled in the Cortex also to give the abstract level of kind of IP usage or the algorithm which are available here. Some of our partners board are available now to do the experiment for the NX devices. Same is the case for the DX and earlier generation devices also here. The architecture remains same, which I have explained here. The GX comes with only the SerDes and the logic, whereas the SX comes added with the quad core A53. TX get added with the PAM4, which is basically enabling SerDes, taking 28 to 58 gig in this family. And the MX is basically on top of that. DRAM, which is basically HBM2, has been added here to give you the higher bandwidth memory access. It can go up to 512 Gbps DRAM bandwidth. Array10 is our mid-range. Still, we are serving to the customer using the Array10 FPGA for the mid-range. It very work for the processing power, which is 1.5 teraflops of operations. DSP functions, which is basically like, this has the first floating point DSP into this particular core. ARM A9 dual core has been introduced here in this. And the earlier generation was also having majorly used for, like, data center networking, automotive, and IoT applications here. Cyclone 10 is the FPGAs, which are basically like, for the using, like, for the IO bandwidth expansion, or the you're looking for the Cyclone 5, which is basically like, improvement, continuation to have the SoC kind of application for the embedded area workload or the targeting that. The details are like, to get from our website, but these are the FPGAs where, like, looking for the low cost, smart, connected systems. Like, we have launched, like, the program also, which is like, enables these FPGAs along with the Max10s for the cloud connectivity for the embedded applications. Max10 is the CPLD devices, which has the huge amount of innovation coming, including, like, analog hardened blocks are there, user flash are there, a Neo soft core processor, which is 32-bit processors are there, DSP blocks are there, memories can be interfaces apart from the internal memory, and flash. It is the flash-based device, so that, like, you don't need to have the external flashes, where the other FPGAs which I spoke required the configuration image to be stored into the external devices, can be a memory or can be an SD card, but this stores its flash within its own device available flash. While doing the innovation into the silicon, it doesn't make sense. It will not be justified if we are not innovating to our software portfolio. You see the software portfolio on the left-hand side. If you start, if you are the hardware developer, if you are the RTL engineer, you know VHDL Verilog, you know some of the RTL language, or you are doing the bare metal application, you have to start from there. Like, quarter suit you have to see. And then, if you're going toward the right-hand side, HLS compiler, will get enabled, parallel compilers will get enabled. And if you go toward the right hand side further, like the software library stacks has been abstracted to the higher level, so that the one API what we are speaking is basically the innovation towards the right hand side. And if someone is using the RTL and the conventional hardware language, left hand side is though. Anywhere you move yourself as a designer, a firmware designer or a hardware designer or a software designer, we have a platform, we have an innovation into the software, and this enables you to use the FPGA without looking at whether I know RTL or not. Like, there are some trade-off are there for sure. Like, if I'm doing on the RTL, I'll be seeing the performance boot. But when I'm doing on the software domain, there is some trade-off, and some of the productivity boost will be there. But, like, little bit performance-wise, we have to be watchful, and we have to see how we are implementing these things. Like, this has been spoken about in the earlier session also. We have a lot of our own as well as the partner boards coming in, which is can be readily available, can be deployed for edge or the embedded application for the communication infrastructure, 5G being like the core application, or front haul, mid haul connectivity, accelerating workload, which is basically like, for 4G turbo or LDPC for the 5G perspective. N3000 is the still we are serving that. N6000 is the next generation which are available for the customer. And if you see that, other right hand side, which is basically like, our cloud and enterprise area where like, all the data center and data centric applications, if you want to accelerate high performance trading, frequency trading, or any other like, database acceleration are few of the example which we have spoken here in this. And these cards are available from Intel as well as from our partner portfolio, which are integrated. Coming to the university program, 4 pillars are the major pillar which we are driving this particular program. We have to enable professors to teach this technology to the student, to the researcher, learn it, students to learn it by way we are enabling them the lab, exercises, board, software, virtual boards are available. We expect like, researcher to make it, break it, don't make this particular infrastructure hardware the beauty of the shelf rather than like, break it. We'll be more than happy to see and hear that, hey, one of the board has gone bad because we were doing this experiment. That's basically like, we want you people to utilize this particular board. A lot of institutes are there and they have these boards in this program, and they have this board there with them. And then who are interested, please get in touch with myself or Padmanabhan. Will do the needful, like, and from this what we want, like, you to become a developer and develop some of the innovation products, IPs, or the indigenous requirements from our government, defense, or local requirement perspective, so that we are utilizing this particular ecosystem. Like, Unity course focused curriculums are available, which is like, semester long lab exercises are there, tutorials, online workshops are available, free libraries or IPs are available for the student to do the project, example designs are available, so that because we are innovating, we are utilizing this, we are integrating this, and we are moving ahead with our innovation. That way we wanted to utilize you people to utilize and enable this particular infrastructure to all of you. These are the software suite which are available, starting from the Quartus Prime, Neos, Model Sim. Now we have a Questa Sim also enabled for the simulation perspective. SDKs for the OpenCL1 APIs also integrated here, and the deep learning accelerator suites are also available here. You see, these are the boards, commonly used board, which are available in most of the institutes for the lab purposes, for the purpose to take up your hands-on exercise in the lab, or take these boards are also virtually enabled. Remotely you can access, no need to be into the lab to access this particular board. See, these are the board which those who are our university partners, we have donated them. We'll continue to help them to how to use this board, and software has been enabled here. Like, so documentation, design example, support for the community, virtual on-demand trainings, which are the accessible access you will be getting to these resources once you are enrolled yourself for the university program. This is one of the snapshot of the digital logic, computer organization, embedded system, AI, or the courses. Many more courses are there. We can do like, co-teaching. We can come sometime, do the talk, do the specific talk. We can run the lab. One API is being one among them. We are running with a lot of institute. A lot of credit courses are there, which can also be the option for you people to choose here. These are the resources, online resources, which are available. We'll be making this particular slide available to all the participants so that you can take a reference. You are not relying on people to come, but these are the recorded sessions which are available here for you to take the institute. So here I would like to stop this session, and if any questions are there, probably I can take up. I'll stop sharing also. Yeah, so there is a question like, Intel FPGA supports Quartus software will support other platforms such as MATLAB, VLib. Yeah, so Intel FPGA supports a lot of virtual platforms. MATLAB, specifically Simulink being one. Through our DSP builder, we supports it. LabVIEW is basically like, it can be integrated by means of accessing FPGAs in a system in loop, HLL hardware in the loop perspective. We can do it in that way. But if you see that, like, other HPC domain or the abstract level tool, which is basically one API, Intel's, like, other tool has been also integrated, which is basically like, profiling tool, optimizations for the FPGAs, what all the tools are required, those are also enabled here. OpenCL, by means of OpenVINO has also been enabled here to use it, that I can say. So what is FPGA uses in real-time world? It's basically like, for the real-time world is FPGAs are the one of the long-time vehicle get used to realize real-time application. For example, like, traffic monitoring, security surveillance, and then, like, security surveillance, I'm not talking of the campus. Within, like, country-wide security surveillance, these FPGAs are used to get the real-time natural language processing system. What is getting deployed, FPGAs are there. So these are few of the real-time examples which I can quote here, but many more are here available. Like, do we need the OpenCL SDK for this program? No need. These are optional one. But if you have a Cortex, you are looking for the RTL design simulation, OpenCL SDK is not required. But when you are looking for the abstract level to get realized for the C++ program, this is required. Yes. Others are there. Question is basically, let me see. I think these were the question for me. I answered it. If any other questions are there, please write into your chat box. Either myself or my colleague, we will help you to get the answers. Firoza ma'am, over to you. And Biplav sir, over to you.
Thank you, Ishla sir.
You're welcome.
In case, dear participants, in case you are having any queries, you can also mail us your queries and we will forward it to our resource persons. So now we are moving towards the second lecture of this day one. It is Introduction to Cortex Prime Design Software. It will be taken by Padmanabham K. sir. So before that, we would like to share his brief profile with you all. Padmanabham sir has postgraduate degree in Applied Electronics from Anna University, Chennai. He has 14+ years of experience in digital design for both FPGA and ASIC. Padmanabham sir is the software enabling and optimization engineer in customer support experience group at Intel PSG. Prior to joining Intel, he worked as chief faculty in Sandipani School of VLSI Design Training Division of Coril Technologies, Bangalore, and as an assistant professor and project coordinator in MS RSAS, Bangalore. Padmanabham sir, welcome to the session.
Thank you so much.
I made you the presenter and handing over the session over to you.
Thank you so much, Biplav, for your warm welcome. Good morning, everyone. Good afternoon. Welcome to the session. I hope you are able to see my screen.
Yes, sir, it is visible.
All right. So good afternoon, everyone. So welcome to the day one of the faculty development program on designing with Intel FPGAs. So we are going to learn about the Intel Cortex Prime design software in this session. I will walk you through the session topics. This session will be extended in the afternoon also for an hour. So let us continue with introduction to the Intel Cortex Prime design software and understand creating and managing projects. Then we are going to see how do we perform functional simulation using the Model Sim Intel FPGA Starter Edition. Then we will understand how to perform synthesis and filter, generating the programming file, which is the assembler file. And then we are going to use the remote console. For setting that, we are going to program the FPGA using our remote console, and FPGA implementation using the virtual labs with remote console. So I'm going to show you the demo, and you can try that hands-on in the afternoon, so that you will get an idea how you can write a digital system code, and then you can access the remote. That means you can upload your SRAM object file, the bitstream file, and you can access the board virtually. Let me take you through the Intel Quartus Prime design software. There are 3 editions in Intel Quartus Prime design software. One is the Lite edition, the other one is the Standard edition, and third one is the Pro edition. Lite edition does not require any license. So for our program, we are going to use the Intel Quartus Prime Lite edition software, and the Standard and the Pro edition requires a separate feature license. So we have given the details of how to download the software, but then still I can just show you. Download center for Intel FPGAs. If you get into the site, we can see that we have the FPGA software download of Intel FPGAs pages, where you can see on the left hand side Intel Quartus Prime design software. If you click that, you can able to see editions. So one is the Pro edition, the other one is the Prime Standard edition, and then we can also see the Prime Lite edition. What we wanted for this program is the Quartus Prime Lite edition. So we requested you to download 18.0 or 18.1 version, because it is compatible for all the 6 days, so that you don't need to worry about different versions. So we request you to download either 18.0 or 18.1. For example, if I just click 18.0 for Windows, or you can also choose for Linux, this will take you to our Intel Quartus Prime Lite Edition design software version 18.0 for Windows. What are the things that need to be noted down here? You can see that Intel Quartus Prime Lite Edition software, it also shows that on the bracket, device support included. So the device support included means the Lite edition supports our Max 10 and the Cyclone 5 devices. So you don't need to download the device support library separately. This 5.8 GB includes the device support also. So you have to download this tar file, and then you can extract the files into the temporary directory, and then you can run the setup .bat file. So once you have the Quartus Prime design software ready, then I will walk you through these steps, like how you can continue with the FPGA design and implementation. I'm going to show the demo, right? You can do the same during your hands-on session, which is scheduled in the afternoon. So this is one, and if you click the individual files here, you can also see if you wanted to download Intel Quartus Prime design software separately, 1.7 GB it is there. If you want to install Model Sim Intel FPGA Starter Edition separately, that is 1.1 GB. And here you can see the device support. If you wanted to do it separately, what I can suggest you is you can have Quartus Lite setup download separately, Model Sim download separately. And you can download only 2 devices. One is the Intel Cyclone 5 device support. Other one is the Intel Max 10 device support, because we are going to use only these 2 devices through our program. So either you can go to multiple download and download one file, which is 5.8 GB. Otherwise, you can select the individual files tab, where you can download 1.1 GB of Model Sim and 1.7 GB of the Intel Quartus Prime design software and Intel Cyclone 5 and Max 10 device. Right. So let us go through the session right now. As I mentioned, that there are 3 editions. One is the Lite, Standard, and the Pro edition, which was explained here. If it is a Lite edition, it gives support for our Max 10 and Cyclone 5 devices, which we are going to use for our program. And Standard edition supports ARIA 10 as well as the Stratix 5 devices. Whereas the Pro edition supports the Stratix 10 as well as the Agilex devices, which were explained in detail in the previous session. So I request you to download and keep the software handy, so that we can perform the virtual labs with remote console, where we can access the board virtually and we can perform the digital system design examples effectively. So this is about the Intel Quartus Prime design software licensing. So as I mentioned, if it is a like edition, there is no change, there is no license required. There won't be any issue if there is with the latest version, because some of the labs are compatible for that specific version, right? So then we need to provide you a different set of lab manual or different set of settings to do that. That's what we suggested, that you go ahead with that. So for the basic labs, there won't be any issues, right? There is no problem. Subscription edition, which is a standard edition, there is no change, and you can work with the same. And when it is a pro edition, then we require a new feature line. What is Intel Quartus Prime Design software? It is a fully integrated development tool, and you have multiple design entry methods. So you can use VHDL, Verilog, as well as System Verilog. The Quartus Prime Design software also supports System Verilog, which is a hardware description and verification language. We can use it for design. And you also knew that we have a Questa Intel FPGA Starter Edition, where you can use System Verilog for verification also. So we do logic synthesis, and then we are going to do place and route, and then we are going to do device program. All the 4 steps we are going to do. Once we generate the SRAM object file, which is the bitstream file, we can upload that SRAM object file to the virtual lab setup also. And what we are also going to see during the demo is how do we use the Model Sim Intel FPGA Starter Edition and perform the functional simulation. So the Intel Quartus Prime Design software features, if you see, it is an operating system support like 64-bit Windows and Linux support. And you can create a new project wizard. I'm going to show you how that could be created. We have different set of design entries, right? There was a question on the MATLAB and Simulink support. So the answer was given that we have a DSP builder for Intel FPGAs. Similarly, you also have an Intel HLS compiler, which we are going to discuss in detail on Monday's session. So we will see how do we convert a C or C++ code into an RTL. Not only directly, we are going to use Verilog, VHDL, and System Verilog. And on the constraint side, we can apply pin constraints as well as the timing constraints. And we also have a third-party EDA synthesis tool support that is also available with the Intel Quartus Prime Design software. And there are different debugging mechanisms and different set of weavers I'm going to show you, like RTL weaver, technology map weaver after synthesis, and then fitting operation. And then we are also going to see the state machine weaver. Right, and then we have power analysis, and then we use static timing analysis, how to perform timing analysis using the Intel Quartus Prime Timing Analyzer. We are going to discuss in detail how to perform timing analysis and how to ensure that the design is not having any setup or hold violations. We will discuss that in detail in tomorrow's session. And we are going to discuss about simulation. There is a specific session on simulation and debug, where we are going to use the different hardware debugging tools like Signal Tap, Embedded Logic Analyzer, and then we are going to discuss about the system console, right? All those things during our 6 days FT. Let us start with the Intel Quartus Prime Design software. So let me directly open the tool and then we can start working on it. So if you open the Intel Quartus Prime Design software, if you go to the Help tab and then see About Quartus Prime, you can see the version here. You can see Quartus Prime version 18.1. It also shows the build, and then it shows which is a light edition. Now, what are the things that need to be noted down here? If you see that you have the Project Navigator tab, which is the hierarchy. And then we have a task tab, as I mentioned, that what are the different tasks we are going to perform. Similarly, analysis and elaboration, we are going to perform synthesis operation, we are going to perform FITR, which is called placement and routing. All those operations, which tasks are completed and which tasks are in progress, that we can see in the task compilation tab. We also have a tickle console. At this junction, it is not required. Let me close that, and then I will explain when we try to do the pin planning. So we can see there is a message tab, and then you also have a critical warning and errors tab. Like based on the kind of code what you do, we can see the critical warnings here and the kind of error messages, and then we can also see the warning messages that is given in the message window. And on the right hand side, if you see, you can see the IP catalog, which is called as Intellectual Property Catalog. where you can have multiple functions. That means they are pre-designed, they are pre-tested, and then they are pre-verified. We have basic functions, we have DSP functions, we have interface protocols, memory interfaces and controllers, processors and peripherals. All those things are there, which we are going to discuss in detail during our program. And if you see here in the blue screen, you can see recent projects, which projects we have created recently. Those projects would be listed in the Intel Quartus Prime Design software. And if you wanted to open a project which is an already existing project and it is not listed in the recent project, then we can click open project and open the Intel Quartus project file, which is the QPF file. So since we are going to open a new project wizard, we need to just click new project wizard and then we can create the specific project. So our main logic is to understand how to create and manage the projects in the Intel Quartus Prime Design software. What is very important also for us is like, what is the kind of target device family which we are going to target? As I mentioned earlier, that the Light Edition supports the Max10 and Cyclone 5 devices. Right, we can just start with the Max10 library, and then the another example which I'm going to show you the demo would be on the Cyclone 5 device. What is required to be handy with us is like we need to ensure that the specific logic, right, the scenario that we can write it out. So I will explain that to you right now. Here, if you see, you can search here DE10 Lite manual. This is the DE10 Lite user manual, which is from our distributor called Classic. What we wanted to do here, this is based on our Max10 FPGA, which is ideal for all digital logic design labs. Because this DE10 Lite board has 10 switches, it has 10 LEDs, and then it also has 6 hexadecimal displays, and then it has 2 buttons where you can use it for ideally for all digital system design applications. And what is very important for us while creating the project is what is the family device filter that need to be chosen for the corresponding device. You can see that the Max10 stands for, that is 10M, that is a Max10 device. 50 stands for 50K logic elements. Your logic element is one, which is a combination of a 4-input lookup table plus 1 register. That's what we call that as logic element, LE. So now you can see that 10M50, that means it has 484 pins and it is for the commercial application. 7 is the speed grade. All these informations we wanted. Whenever we wanted to create a project, we should know that what are the basic resources that are present inside the FPGA, like lookup table, which is the basic component, and then we call that as an adaptive logic module, which is called as an ALM. Right, we should know about that because an adaptive logic module will have an 8-input, right, lookup table. And then it have a 2 3-input adders, and then it also have 2 registers. We call that in terms of ALM. And what is also required for us is to understand what are the memory resources and the digital signal processing resources that are present in this. So at this junction, let us understand that you have a memory which is 9K memory. So 9K stands for 9 into 1024. That many bits it can take it like that. And also you can see there is a 18x18 multiplier that is available for us to perform any multiplier and accumulate kind of operations, right? So let us first start with basic examples. Therefore, we need to know that what is happening inside the Quartus Prime Design software while creating and managing projects. So what is important for us is to understand only the family filter while creating the project, because when we are going to implement the design onto the board, it is very essential that we target it for the corresponding device family. What we need to do is like we should click new project. The moment we give new project, it takes us to the new project wizard where it helps you to create a new project and the preliminary project settings, including the following. So what is very important for us is to give the details about your project, the project name and directory, name of the top level design entity, project files and libraries, target device family and device, as well as we should provide the EDA tool setting. So all these information need to be provided. Let us understand that what details are required at this junction, and the other details we can provide whenever required while during the project. Let us start with next here. Now this is the page where we need to create the new project wizard. So here we need to provide what is the working directory for this project, and what is the name of this project, and what is the name of the top level entity for this project. So if you're going to create a new directories, you can say in the C drive, I create a new directory, for example, IIT, right? And say G and say FTP and say, for example, example1, something like that you take. So inside this directory, we wanted to create a project. What is the name of the project? For example, I say the name of the project is a gate, something like that you take. I say here logic gate. Now you know that from Verilog, the file name and the module name should be similar, right? So now the moment you say what is the name of the project, automatically it takes that as the top level design entity. So what are the informations that need to be provided? What is the directory, and what is the name, and what is the top level entity that we have provided? The moment we enter all these details, we click next, and this takes to our page where you can see there is a dialog box stating that there is no directory existing at this junction. So do you wanted to create it? You should say yes to create a new directory for us. And now this page is very, very important for us, right? So I will just stop here to explain the details so that you can make a note of it. Now in this, there are two things you can see. One is called select project to create. One is an empty project. The other one is the project template. What is given in the empty project when you say we are going to create a new project by specifying the project files and libraries, target device family and device, and then EDA tool settings. So since we are going to create a new project at this junction, it is better to start with an empty project. Once we have the hold and have some idea of how to create and manage projects, it is better that we can directly take a reference design template, which is called as a project template. So this would be available as an existing design. So let us start with the empty project, and then we will continue the steps one by one. The moment we say empty project, the moment you say next here, it is asking you to add the file. There are two important things here. When we are creating a hierarchical design, for example, using a full adder, you are going to design a 4-bit triple carry adder. And using that 4-bit triple carry adder, you are going to design a multiplier. Then you may need to add the submodule files in the add files option, because you wanted to add the design files, which we need to get included in our project. Okay. Sometimes you need to add all the files. So you can just say add all and all those files. But at this junction, since we are going to create an empty project, there is nothing to be added at this junction, right? But then when it is an hierarchical design, it is very critical and important that we need to add it. Similarly, sometimes you need to take the files from the system design, and that need to be brought into the Intel Quartus Prime design software. In that case also, it is very critical and important to have this tab. So the moment you say next here, it is taking us to the family, device, and board settings. What is very important for us here is to select the family, what we wanted. As I mentioned, and then we downloaded the DE10 Lite lab manual, which is for the Max 10 device. I request you to select the Max 10 device. The moment we select the Max 10 device, on the name filter, we are supposed to type the family details. So 10M50 DAF 484C7G. That you can see that. So it is providing the detail of the FPGA family, what we wanted to be target for. Now you can see the details here, 10M50 DAF 484C7G. Select the corresponding device and then see the details here. Number of logic elements, it shows 50K logic elements. You can able to see 49,760. And total number of IOs, input outputs, and then you can also see the memory bits. Also, you can see the embedded multiplier 9-bit. So you can see 144 into 18 cross 18 or 288 9 cross 9 9-bit elements are available. What is important for us is we need to select the corresponding device, right? Once we select the corresponding family, we can say next here. Now, this particular tab also have two important informations to make a note. One, you wanted to provide the simulation tool which we wanted to be used for performing functional simulation could be provided in this case. For example, you can see that it supports Active HDL, Rivera Pro, Model Sim Algebra, Questa Sim, everything. As you know, that when you install the Quartus Prime design software like edition, it also has the Model Sim Intel FPGA software, right? That is installed, right? That means it is integrated into the Intel Quartus Prime design software. So if you wanted to use any other simulation tool, then we can specify that also in the EDA tool settings. But then we wanted to set it later. Yes, that provision is also available. So the second one, what we need to note down is we can set the provision here or we can set them later. So since we are creating this, now we can set the information of the simulation later. Okay. So we can give next here. Now we can see the summary. When you click finish here, it shows that the project will be created with the following settings. So now we can see what is the name of the project directory. It clearly shows that what is the name of the project and what is the name of the project name. And then we can see what is the family name that has been targeted for it. Was 10M50 DAF 484 C70. The moment you get this summary page, we can click finish here. Okay, all right. So now we can create a new specific file, whether it can be Verilog or it can be VHDL or it can be system. Let us try that. How do we need to do? When you say we need to go to file and then we go to new, and here you can see whether you wanted to use a system Verilog HDL file or a Verilog HDL file, or you can also see there is a VHDL. What we wanted to test is the Verilog HDL file. You can also try definitely system Verilog HDL file as well as the VHDL file. Let us start with a simple example and then I will show you how others can also be incorporated. The moment you select the Verilog HDL file and say OK, you can have a space where you can provide the details of your Verilog code. That means you can enter your Verilog HDL code here. So as we are very sure that what is the name of the entity that has been provided, let us go ahead and then develop a simple code now. For example, I say module, and then what is the name of the module is logic gate. So that is the name of the module. And then I just say take two inputs and then just say one output. Let us take that output Y. And now we can just say assign Y is equal to A and B. That's all, and say end body. What we have done now is it is a simple code. I have A, B are the inputs. You can see that. And Y is the output, and just I use an AND gate, assign Y equal to A and B, and then I provided the end module here. How do we save that once you provide the space and then we have developed the code and then the code is ready? It is our responsibility to save it with the Verilog extension, right? That is .b. How do we save this? So please ensure that the name of the file should be logic_gate because that is the name of the module. So we can go here, file, and say save as. And so you can see here logic_gate.b. You can say save. Now, what is very important for us is how do you know that the code what we have written is not having any syntax or semantic errors? If there is any syntax error, then I need to rectify that, or I wanted to check whether the Quartus Prime design software provides the errors or warnings based on our RTL code. So how do we cross verify that? You can see on the top, there are multiple play buttons and symbols that are available. We are going to learn them in detail later. But at this junction, you can see there is a play button which is called compilation, which performs all the process at a stretch, which is analysis and elaboration, synthesis, filter, and it generates the programming file also. But we don't want to do everything at a stretch because we are creating a new project and then we wanted to go step by step. What is the first step? What we are supposed to do is we need to perform analysis and elaboration. The analysis and elaboration steps elaborates our code and checks is there any syntax error. So that means it performs initial synthesis. That's what we are going to do right now. This is a symbol which we need to click here. You can see that the moment you keep the mouse there, it shows that start analysis and elaboration. We can just run that. On the task tab on the left hand side, you can see what is the percentage it takes and what is the time that has taken to complete that step is also provided. You can also see on the right corner that whether it is completed 100% or not. Now you can see it shows 100%. Right, so now we have performed analysis and elaboration, that is done. And what is the necessity of performing this analysis and elaboration? That has been explained to you, because this code is not having any syntax or semantic errors. But then if it has an error, then how the Quartus Prime design software is going to show us, that also we will see. Now it shows that the Quartus Prime analysis and elaboration was successful, and then it shows 0 errors and then 1. Let us add an error and see what happens inside the design, right? So now let us remove the semicolon from here. And then we save the file and we perform analysis and elaboration one more time. The moment you perform analysis and elaboration, you can see that there is a Verilog HDL syntax error at the line number 8, because it shows that near the text where there is an end module, it is expecting a semicolon. That means there is a semicolon which is missed in the code. That's what it is providing. What we can do right now, so again you can go back and add the semicolon, then we can save the file and perform analysis and elaboration once again. Once it completes 100%, we need to see the RTL schematic. That is the step which is very critical and important for us. How do we perform the RTL schematic? Let us explore that. Now you need to go to Tools, and then we should select here Netlist Viewers, and then here we should select RTL Viewer. I'm showing it once again. Slowly you can see that. Go to Tools, go to Netlist Viewers, and then we can see here RTL Viewer. The moment we open the RTL Viewer, we can see that there is an AND gate. That means you can see that we have given A, B, and then we have taken Y, so that it provides the RTL schematic of the design. Now, what is very important also for us is like the code what we have written is also providing the same functionality or not. That means you know that from the HDL perspective, there are 3 important characteristics that is present in the HDL. So one we call that as the simulation, the other one we call that as a synthesis, and the third one we call that as a documentation, where we call that as a design reuse. So what is very important for us is to ensure that the design provides the intended functionality. For that, we need to perform functional simulation. So without performing the simulation, we cannot guarantee that the code is working as per the intended functionality. What we are going to do, we are going to pass some test vectors and ensure that it provides the correct output. So for that, what we generally do is like we create a test bench. What is very important here that you have a Model Sim Intel FPGA Starter Edition that is integrated with the Quartus Prime design software in order to help us for performing functional simulation. So let us write a simple test bench for this design, and then I will show you what are the 2 important steps that need to be kept in mind while performing functional simulation with Model Sim. We will try that and ensure that the code is working fine, and then we will move back to the presentation. Whenever you wanted to create another file, again you need to go to the File tab here and select File and then new, and open again Verilog HDL file. The Verilog HDL file, what we are going to create right now is a test bench, which verifies the function. So we all knew that a test bench is a top-level module without any inputs and outputs. So therefore, there is no input and there is no output. Let us start with that. So now what we wanted is we need to write logic gate. So I suggest that you write a TB, which is a test bench. What is the first component? It's the data type declaration. So reg AB, and then I say wire Y. That means A and B are the inputs that is given as reg, and then the output is Y, which is a wire. Then we need to do module instantiation. That is the second component. You all knew that we need to use either positional association or named association. Whereas in Verilog, what is recommended is to use the named association. Let us follow with that. So dot A is connected to A. Then we can say B is connected to B. Right? And then we also should ensure that the Y, that means your output should also be connected to the output. So dot Y is connected to Y. Now you can see A is connected to A only, B is connected to B only, and Y is connected to Y only. So we have provided the module instantiation. Then we can say procedural block declaration, initial begin. Now we need to provide the test cases, right? Which test cases are required. So I say at the 0 time unit, the values of A and 0, right? That can be same, but then we can modify it later. At 5 time unit, I want A to be 0 and then B to be 1. And later after 5 time unit, I can say A is equal to 1 and then B is equal to 0. And again after 5 time unit, I can say A equal to 1 and then B equal to. So you can see all the 4 cases we have provided. So we can see data type declaration, module instantiation, procedural block declaration, test case generation. And then we also need to know how to see the output. For that, we require a display statement. Even though it is optional, it is recommended to see that in the console, right? What is happening at a specific time. We use $monitor, which is a system task. So initial $monitor, $time, then we can provide the values. We wanted all the values in binary. So A equal to %B, B equal to %B, and say Y is equal to %B. Then we say A, then B, then Y. And say end module. So here you can see all the 5 components of the test bench we have developed: data type declaration, module instantiation, procedural block declaration, test case generation, and also the display statement. So we can save this file and say file, save as, and please ensure that you save it with the same name with underscore TB, so that it's very easy for you to trace out later. So logic underscore gate underscore TB dot B, I say save. Right, so you can see that our design is logic underscore gate and the test bench is logic underscore gate underscore TB. Now, whenever we develop the code, it is our responsibility to perform analysis and elaboration one more time. That is very critical. If you see here, analysis and elaboration, it shows a question mark on the left-hand side. That means since we have updated our test bench file, it is our responsibility to perform analysis and elaboration one more time. How do we need to do that? We can again go back and then click the analysis and elaboration so that we can check are there any syntax errors in the test bench. Okay, right. So now till now, we developed the code, we developed the test bench. What is very important for us is to ensure that the code is not having any functional errors, right? So as I mentioned that we are going to use the Model Sim Intel FPGA Starter Edition. But before using that, there are 2 important steps that we need to do after installing the Intel Cortex Prime Design software. It is our responsibility to do 2 important checks before performing simulation. The first one is in the tools, right? In the tools, the tab, click tools, and then you have to go to options. So tools, options. If you open that, we can see on the first, right, you can see on the left, you can see select the first one, which is called as EDA tool options. In the EDA tool options, on the right hand side, if you see, what we wanted is the model sim Altera. You can see that the path is already specified, right, in my system. But when you open it for the first time, it would be blank. What we need to do is, you can see on the right hand side, there are 3 dots. You have to click that. And you should go to your installation directory, where in the Intel FPGA Lite, in your installation directory, you can go into the 18.1 folder, where you will have model sim, right, which is the Intel FPGA starter edition. Inside that, you have to select Win32. So this path need to be selected. And then when you say OK, automatically the path for the model sim would be set. If you are running simulation without performing this step, what will happen is, you will be getting an error because the model sim does not know where the executable is set. Okay, so in your installation directory, you can see under Intel FPGA Lite, where you have installed your Quartus Prime design software, you can go to the version. Which version? Inside that, you can see there is a folder called Model Sim ASC. Inside that, you need to select Win32 LOEM. That is important. So please ensure that step is there. That means it is given. So if you go through the options, you can see we need to specify the directory. Contains the tool executable for each third-party tool. But for our case, right, for today, we require only the Model Sim Intel FPGA Starter Edition. So we don't want to specify any other path. We are going to just update the last one. Please ensure that this path is set. This is number 1. The second one, what we are going to do is, like, we need to configure the test bench, which is very important for us. Right? How the compiler knows that that is the test bench, we have to provide the detail now. We should go to Assignments tab, and we should click Settings. In the Settings tab, you can see there is a tool name. We have to select here Model Sim Altera. So tool name, and we have to select Model Sim Altera. And in the compile test bench option, right, you can see after selecting tool name Model Sim Altera, we have to come here and select compile test bench. The moment we select the compile test bench, on the right hand side, you can see test benches. Click that. That will open a dialog box where we should say new, and we have to enter the name of our test bench. So logic underscore gate underscore TB. That is the test bench. The moment we provide the name of the test bench, automatically it will take that as the top level, because we knew that a test bench is a top level module without any inputs and outputs. So after it provides that, you can see there are 3 dots on the right hand side here with the test bench and simulation files. We click the 3 dot and we have to select our test bench file, which is logic underscore gate underscore tb.v, and we should say open. Once we open the test bench file, on the right hand side, you have to click add the test bench to our project, and click OK and close all the dialog boxes. OK, the last one, you click apply, then you save. Now we have configured the test bench also. What are the 2 steps? First thing is, we should perform analysis and elaboration and ensure that the code is not having any syntax or semantic errors, number 1. Second thing, what is very important for us to note down is we should specify the path, right? And then once we specify the path, it is also very critical and important for us to ensure that in the EDA tool options, right, we have to check whether the path is set, as well as in the simulation, we have to configure our test bench properly. Now, once we do this, we can perform the simulation process. To perform the simulation process, we should go to Tools, Run Simulation Tool, and you should select RTL Simulation. So Tools, Run Simulation Tool, RTL simulation. This is what we should select. So the moment we select that, we can see there is a Model Sim Intel FPGA Starter Edition which comes here. You can open that. And you can see the outputs here. On the right hand side, you can expand and see whether all the values are applicable that you can check here. When it is 1, 1, what is the output? You can also see here in the console, right? You can see in the transcript window, when A is 0, B is 0, Y is 0. When A is 0 and B is 1, Y is 0. And you can see when A is 1 and B is 1, you can see Y equal to 1. On the left top, you can see that it shows a Model Sim, which is an Intel FPGA Starter Edition. And you can also trace the waveform here by saying that, okay, when A is 0 and B is 1, what is the value of Y, which is 0? These informations, you can see that. If you want to close only the Model Sim Intel FPGA Starter Edition, yes, we can close it. And we can continue with the Quartus Prime design software. Okay. So whenever you have completed the functional simulation, then we feel that this Model Sim Intel FPGA Starter Edition is not required, then we can close that. You can see that close this separately. Are you sure you want to quit? We can say yes. Right. Now let us go through the presentation and then continue the remaining steps. Right. So I can definitely show the new project creation process. Let me close this and then open once again. Whenever you click a new project wizard, it will ask you for the new project name and directory, name of the top level design entity, project files and libraries, target device family and device, and the EDA tool settings. So click here, project name. For example, I wanted to create an example 2. I say example 2. What is the name of the project? For example, I say counter. And you should say next, because it is a new directory. Once you give that, please ensure that you select the empty project. That is important. Once we click empty project and say next, in the add files tab, we don't want to add anything. But what is important here is, like, if you are creating an hierarchical design, then it is important. Otherwise, it is not necessary. Now you can click next. So this is very important for you. Where the important information is, you have to select the corresponding family. As I introduced only Max 10 so far, I request you to select the family here, Max 10, and on the name filter, if you are not very confident, directly open the DE10 Lite lab manual and copy the family filter from NM50 DAF 484C70. The moment you enter the family filter details, you can able to see, right? It is the specific FPGA board, right? That comes there. Click next. And you don't need to select anything in the EDA tool settings. Say next. And you can do summary. In the summary, what are the two important things we should refer? What is the name of the project directory? What is the name of the project and the family name on which device you have targeted? Then you can say finish. So this is the way how you can create a project. Right? Now if you want to continue, yes, you can continue by saying file, new, and then Verilog HDL. Right? If you wanted to close it, yes, you can close it. You can close project. Okay. Now, if you have closed a project and then you wanted to open a recent project, then you can see that the counter is a recent project which we opened some time back. Before that, you can see our project was a logic gate. Okay, you can see the extension which is called as a .qpf, which is a Quartus project file. Now, if you wanted to open the logic gate, you can just click that .qpf file. It will automatically open for us. So if you wanted to open the recent project, automatically you can open that. And then when you double click, you can see the module. But if you wanted to see the module as well as the test bench, then instead of hierarchy, you select here files so that you can see the .v file as well as the test bench file. Both would be available. If you wanted to continue, anything with this design, then you can perform analysis and elaboration, then we can continue the steps, right? We wanted to just leave and close it, then you can close it, not a big deal. So if you wanted to close it, yes, we can do that. So what I have done, how to open a recent project I showed you, that means it is already available, right? That is listed here. And then how to open a new project wizard that we have seen. The third one is that is not listed in the recent project, but I wanted to open a project which I have created some time back, when you say some 10 days before or 15 days before or 1 month before I opened it. Can we open it? Yes, you say, yes, we can. So for that, what we are supposed to do is like we should click here, open project. It will automatically take you through something. For example, I wanted to open a project, which is FPGA example 1, right? This is the folder. Inside that, you can see there is a QPF file, which is called andget.qpf file is there. So this is a Quartus project file. So if you wanted to open an existing project, which is already available, that project we can open it. These are the ways how you can open the project. So here you can see the code, you can see the test bench, everything is there right now. Now, the moment you complete it, you can say close project. There is one more option to open the project. Here you can say open project, or you can also see here recent project. From the file tab also, whichever you want, you can. The moment you complete the project, you can click here close project, and then you can close the project. Right. Let me walk you through some of the presentations, and then we will do the rest of the step now. So what are the things I explained you about the project navigator, about the tasks window, about the tool view window, and then we have the IP catalog, and then we have the messages window, right? So we didn't touch anything on this side, which we will do it during our course, but then we know that what is present in the project navigator, what is present in the task window, and how do we type the code in the tool view logic, and then the messages window, which is important. And we can specifically take all the toolbars one by one and then check each and every symbol. So I will walk you through that later, but then you can check right now. So we need to perform pin planner. That means we need to do pin planning. Then we are going to use this shortcut, which is a pin planner. The symbol is provided here. We have a pin planner. We are going to see the compilation report, which shows that how many lookup tables and how many ALMs are used by this design, how many memory resources are used, and how many DSP resources are used. All these informations you can see in the compilation report. And then you have a platform designer tool, which we will discuss in detail starting from Monday, Tuesday, where we call that as a system integration tool. How do we create a system using the platform designer? And then you are also going to see how to use the intellectual property, which is an IP catalog. There are multiple toolbars that are available, which are present in the main toolbar, and then you can also use them effectively. Right. What is very important for us is like we need to know which window and how do we use it. For example, you have multiple windows. I showed you about project navigator window, compilation dashboard, and then we can use these windows to perform specific set of operations. You can see that. You can attach them and detach them. For example, you wanted to maximize that and then you wanted to minimize it. We can do that in whatever fashion we want. Right. So you have multiple steps at this junction. I'm showed you only minimal. While getting into the details of the Quartus design software in today's session, as well as in the afternoon session after doing hands-on, you will be coming to know that what is the specific logic that is happening in each and every step, and what is the necessity of each and every step, and what is the flow that you will automatically come to know. Right. So what are the informations we should remember is like how to create a new project chart. That is what we should know. We also have a file called as the QSF. This is called as a Quartus settings file, right? Where you can target it for a single device. So everything will be present into the settings file, right? And then you also have a Quartus database file, which is a DB file, which has the compiled netlist information. Everything will be available. So once we open a specific directory, I will show you what are the list of files that are available inside the directory. Let us see two important things like what we have done in the earlier case. We know now how to create a new project wizard, and we also know how to open a recent project, And then we also know how to open an already existing project. Let us go through that in the session right now. How to open a new project wizard, I explained you what is the name of the project and then what is the name of the top level entity that has been explained. And I asked you to create an empty project, no need to select any project template. Later we will understand what is present in the project template. After selecting the empty project, it is our responsibility to select either VHDL or Verilog or System Verilog, what is important for us. So we can add the files if we wanted, otherwise directly we can say next. In our case, we clicked next directly because we don't require any other files. And in the device selection, this is very critical and important. As I mentioned, it is our responsibility to add the name filter. If you are very sure that this is the name filter in the list directly, you can select it. If you are not very sure, then you can directly go to the corresponding lab manual, copy that family filter and paste it here so that it can choose the proper device. Sometimes you are not very sure, then you can type some of the family details. For example, you can type till 10x in AX, which is the ARIA FPGA, right? So you can say AX 1111. That means then automatically you can see the list of devices. Whichever device you want, you can select appropriately also based on the filter device list. We didn't choose any EDA tool settings in this case, but then it is also possible to select the Model Sim Intel FPGA Starter Edition for performing simulation, which I showed you the demo some time back. And once you perform summary, that means once you click summary, that means you can start creating the project. So what we have seen so far is how to create and manage the project. That's what we have seen in the Quartus Prime design software. That means we performed analysis and elaboration, and we also did functional simulation of the design. So what is very important going forward when you say how to open an existing project, that's what I showed you. From the file menu, you can click here open project, which will help you to open an existing project. Also, I showed you what are the recent projects that are available, where you can see the recent projects that is specified. And you can see there is a QPF file where you can double click the Quartus project file where you can directly open that. So I showed the demo of this also. And I also showed you where the recent projects are listed, where there is a QPF file. Also, we can click the recent projects which are highlighted in blue in the Quartus Prime design software. So in all these cases, it is very easy for us to do that. So these are the major steps which we perform. Okay, right. Now the question is like, I don't want to write the Verilog code. Is there any language template that is available in the Quartus Prime design software where I can directly insert the template and then perform some operation? When you say yes, that is also possible, right? So for example, you don't need to develop the Verilog code of some specific logics, or you may not be very much sure whether that syntax is correct or not. You wanted to see a reference and then you wanted to try on your own later, or you wanted to customize that code for a different set of applications. That would be possible, right? What is another way of developing the logic? That's what we are going to say, which we call that as an insert template option. Okay, I will show the demo of that and then we will continue the remaining. So I will directly open the Quartus Prime design software and then we will create a new project and then we'll continue the remaining steps. So what are the changes between the earlier demo, what we have seen, and what is the thing we are going to see now? I will explain that to you. We click new project wizard and we need to see the project name and directory, everything. Just select, okay, whatever we want. So for example, FPGA example 1, I just say example 3, right? And say language template, something like that you take. Now what we wanted is, I wanted to take a memory code, right? I wanted to take a memory code. What is the name of this project? I gave memory. What is the name of the top level design entity is automatically taken as memory. Okay, so you can give any name. I have just given here FPGA example 3 language template. That means 1 and 2 we have seen. So this is related to the third example. Let us say next you create it. You please select the empty project. There is no difference. Add files. Here also there is no difference. Instead of selecting cyclone files, let us select Max 10, and Cyclone 5 we will discuss in detail in the afternoon session. So we can say 10M50 DAF 484 C7G. You select it. And what we are supposed to do is we need to ensure and create a summary project which is based on the Max 10 days. Okay, what is the difference between the earlier case and this one? When you say, you click here, File, New, and say Verilog HDL, and we don't want to type the code. What we wanted to do in this particular session is we need to perform insert template. What is that insert template option? As you can see here, right? So this is our analysis and elaboration, and this is our compilation tab, right? This is a play button. But now here you can see there is an insert template option that is present in the Quartus Prime Design software. Click that. And on the left-hand side, you can see there are Quartus Prime tickle commands, timing analyzer commands, which we'll see in detail tomorrow, system Verilog section, TCL, Verilog, everything. But what we wanted is the Verilog HDL section. So when we expand the Verilog HDL section, and then you can expand full designs. You can see here Verilog HDL, and I expand full designs, and I can expand here RAM and ROM. Now you can see there are multiple memory codes. Let us understand about the RAM in detail later. But now let us use this opportunity to insert the memory code into the template. Now when you say single port memory, and I say here insert and then close, you can see the entire Verilog code for the single port RAM is available for us right now. We don't want to develop the code right now. So if you wanted to modify the width and if you wanted to modify the depth of the memory, we can modify it. Since we have given the name of the Verilog code as memory, let us just change this to memory. That's all. We don't want to do anything. If you wanted to modify something, it is our wish. Yes, we can modify it definitely, so that it would be helpful for us to customize for a different set of applications. Right? Can we save this file? Yes, you can definitely say File, Save As, and say memory.v, and we can perform analysis and elaboration right now. You are guaranteed that there is no syntax error until otherwise you modify so many things. Otherwise, definitely it will work because it is already a template where you don't want to do anything from scratch. So the insert template option is quite handy and very useful where you wanted to directly use that. Yeah, this definitely, it is available for System Verilog also. I will expand and show you what are the things that are available in quite a moment. Now we can go to Tools, and then you can go to Netlist Viewers, and then you can see RTL Viewer, where you can see there is a memory RAM, right? That means you can see there is a memory available. Right, this is not only the entire code. It is not only for the direct code, right? Sometimes what we wanted is, we wanted to just take this logic for only a set of constructs, right? In that case also, we could definitely use it. Okay, so sometimes you may not be very comfortable in case construct, or you may not be very sure in how to use while or for loop or any looping construct. Sometimes we may not be very sure that how to introduce delays. So those kind of things, like wherever we have a specific set of doubts, where we can go through that in detail. So the full construct is also available, and you can also have a specific set of constructs where we have doubt of. That also can be done. For example, let us create one more test and show you to get a clear picture. Instead of changing the same code, let us try one more. So let me create that in quite a moment. And I'll show that in detail for you. See, since I have selected Cyclone 5, it is not showing any device here. The moment you select Max 10, then you can see the device. Okay. Right. Now, what we wanted is, we wanted to see what are the templates that are available. Right, I will show that in a minute. So, File, New, and say Verilog HDL, and say OK. Now, when you click the insert template, what was the question? Are there things available for System Verilog? Definitely yes. You can expand full designs. Full code is available. constructs where you have only the syntax. For example, the same you can try with Verilog also, right? If I expand this for Verilog HDL, you can see full design. That means the entire code is available. Or else you wanted only the constructs where you wanted to get the constructs for only the statement. For example, I wanted to know the construct of case statement. You can click that case statement and say insert and close. Then you can see that case, end case, insert at whatever constructs that would be written. If you have any issues with respect to case X or case Z or whatever, that also could be taken. So a partial construct can also be inserted so that you can modify the code. If I wanted to have a full construct, that could also be possible. So this is the way how that could be done. And that is very critical and important for us to understand and appreciate the insert template option, which is called as the language template option that is available in the Quartus Prime Design software. All right. These are the different options that are available, and then I will just show the flow and then stop there so that you will understand how do we proceed in the afternoon. So this is our Intel Quartus Prime Design software compilation flow. What we have done so far and what we are going to do, the remaining portion I will explain simply here. So we developed Verilog code, and then we performed analysis and elaboration, and we did functional simulation. What we need to do is like we need to apply pin constraints, perform synthesis, generate a programming file, and we are going to implement that on to the board where the board is physically connected to my laptop, that is demo 1. In demo 2, what I'm going to show you that you can upload your SRAM object file directly to our virtual lab, where the board is already available, where you can upload the SRAM object file and check out. So the board will be available for you in 3 minutes. For 3 minutes, in that 3 minutes, you have to upload your SOF file and then you can check the output. Right. So what would be the focus later would be on the timing analysis. That would be our focus for tomorrow's session. But today our focus would be on understanding each and every step and then generate the programming file, implementing the design onto the board, and how do we implement the same using the virtual labs with the remote console. I'll stop here. If there are any questions, I will take it, and then we will resume the session from pin planning after lunch. I'll stop sharing and then wait for a minute. Please let me know if there are any questions. Yeah, some of the organizers can answer that question because they definitely, I hope the video would be available to you. But do you have any technical questions at this junction? Please let me know. I can definitely answer. It is better to install the Cyclone 5 also because we are going to use that. And I'm going to share the virtual lab link, means you would be getting the lab file. Okay, I will share that link in the chat, as well as I will share the lab PDF file with you. And I'm going to start the session, and I will walk you through step by step. The comment on the frequency of the test bench, right? We are going to discuss about timing analysis. You will automatically come to know how do we do that. But then now you can see there is a board frequency available for each and every board, right? Like Baxton has a 50 megahertz clock. Like that, you have different FPGA boards with different frequencies of clock. But especially on the timing analysis, we will understand that, okay, what would be the operating frequency of the design. There is no specific template available for test bench that it is it won't be automatically created, that we have to do, right? But then when you are going for a higher level designs like HLS, and then when you do with the DSP builder, then test bench will be automatically created. Okay, so what may be the problems if you are not able to create a project? So I need to understand in detail, right? So can we discuss that in detail through do the hands-on session? Yeah, so there is a simulator, right? So definitely there will be a simulator that is available. We call that as a waveform simulator that is available for university, which is called University Waveform Simulator. But then you do not have all the capabilities, right? So that's what we wanted to have a specific simulator, which is required for performing functional simulation. Because when you are going for verification later, there are availability of PESTA Intel FPGA Starter Edition, where we can use PESTA Sim also for verification. Right. So if it's showing that device support included, then you need to go to our website, and then in the individual files there would be a device support, which is a QDZ file. Okay, you download it for Max 10 and Cyclone 5, and in the Start tab type device installer. Then it will ask that where that QDZ file is available, it will automatically get installed. So install Max 10 and Cyclone 5 for both, and you can install them one by one. I hope I have answered that question, right? If you have downloaded the multiple tabs, like instead of doing it individual, then that 5.8 GB file will have the device support also included. You don't need to include it separately. Are there any other questions? Okay, which is preferable, VHDL or Verilog? So like that we cannot say right now, right? So both are same only. But now, so which also comes easier also we should see for us, because Verilog is directly from C, right? So you would have a good hold on C, right? Then you feel that it is easier to learn Verilog than VHDL, right? So we cannot say that, okay, this is better or that is better. Both are hardware description languages, and both have all the three characteristics which I possess. Right, so I hope all the questions are answered. Regarding the virtual lab, I will share the details with you in the afternoon. Over to the organizers. Max 10 and Cyclone 5. Cyclone 5. Yes.
Okay. Thank you, Padmanabhan, sir. So now we can go for a short lunch break. We will again rewind at 1:30 p.m. Dear participants, you don't get disconnected. You please stay connected. We will again restart the session from 1:30 p.m. and the session will be on FPGA design and implementation. It will be taken by Padmanabhan, sir.
All right, yeah. Thank you very much. So we will resume the session at 1:30 p.m. Right. Go for lunch and come back.
Thank you, Padmanabhan, sir.
Thanks. Hi, Vipula, shall I start the session?
Yes, Padmanabhan sir. You can start the session.
All right. Yeah, thank you. Let me share my screen and then we will continue. Good afternoon, everyone. Welcome back. The Intel Quartus Prime Design Software FPGA design and implementation session, where we are going to perform synthesis and filter operation implementation and generate the SRAM object file. And then we are going to implement onto the board where I have connected the board physically to my laptop. In another demo which is called as the remote console, I'm going to show you how we can access the board remotely. Right. So as discussed earlier, we can see that we need to perform the analysis and elaboration step, which we did, and we also performed functional simulation. Now we need to apply pin constraints to the design. And then we need to do synthesis and filter and generate the assembler, which is the programming file. Right. How do we apply the pin constraints? Let us start that. Before getting into the details, we need to just go through two important slides. One is what is the logic behind the synthesis, or what is the synthesis step, and we also need to understand what happens in the filter operation. Let us understand those two slides and then we will go back and continue the process with the same design. What is synthesis? If we say it translates the HDL source files into an Atom netlist. Therefore, when you are performing synthesis, the code would be converted into an equivalent gate level schematic, like what we have seen the RTL schematic. That is the technology independent schematic. What we are going to see after synthesis, which is like technology dependent, where you are going to see in terms of lookup tables, that is logic cells, D flip-flops, IOs, RAMs, that is on-chip resources, then DSP blocks, etc. So we are going to see in the synthesis process that it converts the HDL source files into an Atom netlist, where we can see that as a synthesized netlist. The second process what we need to do is called as the filter, which is called as a placement and routing process. So we need to place the components and then we need to make connection between the components. So what is the very important logic here is like we need to perform placement and routing that has to be done stage by stage. There are 4 stages available in the filter. One is called as the plan, other one is the early place, and then we have place, then route, and then finalize. Now, which is an advanced place and route engine for finding a valid solution in a reasonable amount of time. That means if you wanted to perform filter operation, we need to do that step by step. So first we need to do plan, second we need to do early place, then we need to do place, then we can do route and then finalize. You can see that on the right hand side, you can see CP, which is called as the checkpoint. It is also called as a snapshot, which is called SS. Why do we need to do this filter operation in steps? Let us understand that. When you are working on a complex design and then you click filter operation, it performs plan, early place, place, and route, everything at a stretch. What happens at the end of the day, like after running for 8 or 10 hours, it will finally say the design is not meeting timing. So it will be a very tough task for us to apply some techniques after the implementation is done. Right now, what is the advantage here is you can check the output of the quarters at the end of early place. Before placing, you can check whether the design is meeting timing and everything is perfect. Once it is fine, then we can make the tool to perform placement and then we can do routing, then we can finalize. In this case, the prior stages must be completed before running the later stages. So we can run that step by step. That is the advantage of a filter operation. Now you can see that output of each stage is called as a database and that is referred as a snapshot, which is called SS. And it is useful for us to perform incremental optimization. So what we can do is at every point, you can store the checkpoint. You can optimize the design at every checkpoint and then we can run it. In that case, what is the advantage is we can save the compilation time because you don't want to do everything at a stretch, but we can do that step by step. Okay, right. Now let us go back to the previous slide, like where we discussed about the synthesis and filter operation. What we are going to do for the design, what we have right now is we need to apply the pin constraints. Then we should perform synthesis, and then we should perform filter operation. After performing these steps, we can try to generate the assembler, which is the programming file, and we implement the design onto the board. Let us continue that. Let us open the Quartus Prime design software and continue the program where we stopped. Logic gate example we will open now. Okay, right. Now let us perform analysis and elaboration. Right. Now, if you go through the Quartus Prime design software, we can see that the contents, if you go through here, we need to see the pin constraint for this particular device. Where we can select pin constraints here, I will let you know. If you go through the lab manual, right, which is our DE10 Lite, where we can find the pin constraints for this specific FPGA board. So let us start from there. We have push buttons, and then we have LEDs, and then you also have the slide switches that is available. You can see here it shows user-defined slide switch, where you can see there are 10 switches. And what we wanted for our design is require only SW0 and SW1, only 2 switches, right? So SW0 and SW1 we will take, which is pin C10 and pin C11. This is the pin number. For SW0, it is pin C10. And for SW1, it is pin C11. So we require 2 slide switches. And what is the IO standard for those 2 switches is provided here, 3.3 volt LVTTL. And we require only one LED, which is LED R0, which I can take pin as pin A8. Then you can see IO standard 3.3 volt LVTTL. We have to enter these pin constraints to continue synthesis and filter operation. Let us explore that now one by one. Right, so let us go through this pin underscore C10, pin underscore C11 for SW0 and SW1, and pin underscore A8 is for the LED. Right. Let us open the Quartus Prime design software here, and we should go to pin planner. So where is the pin planner available here? You can see here assignments, and then you can select here pin planner. So assignments, pin planner, if you open, you can see this is the Max 10 device, 10M50 DAF484C7G. Right? On the bottom, you can see A, which is an input, but the location is not specified. B, another input, again, location is not specified. Y is the output. So where we can get these locations? The locations are available here. So for SW0, pin C10, and for SW1, which is pin C11, which is nothing but AB. For A, I need to connect it to one switch, and for B, I am going to connect it to another switch. So what we can do here is pin underscore C10. And what is the IO standard here, if you see? So you need to change that into 3.3 volt LVTTL. That is what is specified. Similarly, here you can say pin underscore C11. And again, what I can do, I can select a 3.3 volt LVTTL. And for the output, okay, so it is better to again set the LED, right, where it is pin underscore A8. Okay. So select that now and say pin underscore A8, that is the output. And for that, again, you can select the voltage, which is 3.3 volt LVTTL. Okay, so where did we open is you need to go to assignments, then pin planner. That's all. Assignments, pin planner. If you open, then you will get a page like this. Here in the bottom, you will have the pins like A, B, which are the inputs, and then Y is the output. You can see the directions are specified. What we are going to do is just we are going to provide the location and the IO standard value. Okay, after you specify the locations and the pin numbers, and after we provide the IO standard, what we are supposed to do is we should continue synthesis process and then the filter process. Okay, once you complete this, we can minimize this pin planner tab window and come back to the Quartus Prime design software. And in the task pane, you can see analysis and synthesis. Right click and say start. All right. Now, once the design performs synthesis, there are two important things we should see. One is called as the synthesized schematic. After you perform synthesis, you will be having a schematic which is called as the mapped schematic, which is post-synthesis. And we also need to know what are the resources that are used. Okay, that is in the FPGA resource, right? What FPGA resources are used, that also we should see. One thing is, we can see it shows here total number of logic elements 1, total number of pins 3, and there is no memory bits, nothing is used by our code because it's a pure combinational logic. Now we can go to tools, netlist viewers, select here technology map viewer, post mapping. What we have seen earlier is the RTL viewer, that is before synthesis. What we need to select now is technology map viewer, post mapping. Okay, you can select that. Now you can see it shows in terms of lookup table, LUT, which is the logic cell. Okay. Now what you can also see is when you expand the analysis and synthesis and you click resource usage summary, you can see that how many number of lookup tables are used because it is a 2-input gate. So 4 input functions 0, 3 input functions 0, and it shows that 2 input functions 1. You can see that it shows that there is a 2 input function that is used by our code. And how many number of logic elements are used is also provided. This is at the synthesis stage. During the filter stage, it may vary because it has to place the components and then it has to route the components. Now, what are the things we have seen? We performed synthesis. Before performing synthesis, we did pin planning. How do we do pin planning is we can go through the details of the corresponding FPGA board. For example, in our case, it is DE10 Lite. And then we have gone through what are the pins for switches and for LEDs. And that we have specified in the assignments, which is pin planner. Here we have specified for A, pin underscore C10, and for B, pin underscore C11, and for Y, pin underscore A8 I specified. And then we also specified the corresponding IO standard. Right, you can see, for example, if you wanted to know about what is the kind of IO standard for each and every information, that you can go through that specific device. Okay. After you assign it, you can see the user assigned pins here. You can see that in a different color. And you can see on the right hand side, these are user assigned pins, which are in red color. Okay. So what we have done so far is only synthesis. What is the next step we are going to do is called filter, which is called as placement and routing. Okay, right. So where is the placement and routing option here in the compilation tab? When you say, you can see after analysis and synthesis, you can see filter, place and route. What we can do right now is you can click filter, place and route and say start. Okay, once it completes the operation, again we can see two important things. One is the schematic, which is after placement and routing. Second one, we can see the resource usage summary after filter operation. Okay, let us explore them one by one. Now, what was the fundamental difference when we did synthesis operation? It showed how many resources are used, but it doesn't show that how many resources are available inside FPGA. In that, how many are used? That percentage we didn't see. Whereas that information can be seen when you perform the filter operation. You can see here total number of logic elements. How many are used is 2 out of how many? That means you can see out of 49,760, 2 logic elements are used by our code. And how many memory bits are available and how many embedded multiplier 9-bit elements are available. All these informations we can see. The number of logic elements, memory resources, DSP resources, everything we can see. In that, how many are used, we can see that in the resource summary. But how do we go through the filter schematic? When you say, you can go back to the tools, netlist weavers, and say technology map weaver post fitting. This is post mapping is after synthesis. Post fitting is after placement and routing. You can see that A, B, there is an input buffer, and for the output, there is an output buffer. And then you can see there is a logic cell comp. Right, what we have done so far is we performed synthesis, then we performed filter. Now, what we are supposed to do is we should generate the programming file, which is our bitstream file, the programming file, which is called as an SRAM object file. So we have to perform synthesis, we performed the filter, and then we generated the programming file. So how do we generate the programming file? You can see in the compilation tab, after analysis and synthesis, after filter placement and routing, you can also see the assembler, which is the generate programming file. You can click that and say start. Right click and say start. Right now, you can see inside the output underscore files folder, you can see there is a file called .sof extension, which is called as an SRAM object file. Okay, where it is available, let us find out. Go to the C drive and select the folder which we have, IIT FDP example 1. Inside that you can see DB, which is the database file. And then you can see the QPF, which is the Quartus project file. You have the QSF, which is called as the Quartus settings file. What we wanted to see is inside the output underscore files, right? Remember, output underscore files, when you double click that, inside that file, you can see there is an SRAM object file. This .sof file is the file which we require it for programming our FPGA. Okay, so where is this? When you say this should be present in your directory, where there should be an output underscore files. When you click that output underscore files, where you can get that. What are the other files is you can see the report files which are available after map and after performing the filter operation. You can see this is after generating the synthesis, and this report is after the fitting. If you click this fit.rpt, this is the report which is shown after performing filter operation, after performing placement and routing. You can see all the informations which are required or which are required for us, and we can note it down what happens after the filter operation. Right? So this is for the synthesis, and this is for the filter operation, which is the RPT file, which is the report file. Okay, now what is our next step? When you see, if you go through our Quartus Prime design software tool flow, what we have done is like we need to perform synthesis, we performed filter, and we generated the programming file. When we generated the programming file, we can implement the design onto the board. That's what we are going to do now. To implement the design onto the board, there are two different variants I am going to show you. The first variant is I am going to connect the board to my laptop, the D10 light board, and then I'll show the output. What is the drawback in that is, you can see in the screen that it is 100% successful, but what you may not know is which switch I am changing and which LED is glowing, that you cannot find out. Why? Because you cannot see the board, right, which is connected to my laptop. In order to overcome that drawback, what we are going to do is the next lab demo, which I am going to show you, which is called as the virtual labs with remote console, where you can see the board on the screen and you can upload your SRAM object file and you can verify the output. The same lab manual and the lab links would be shared with you immediately. I request everyone to check that and ensure that you get an idea of how we can access the board remotely. Okay, so to get into that step, right, first we will finish the traditional step. I am connecting the board to my laptop right now, and we are going to do the last step, which is called programming. Right? What are the things we have done? We have done analysis and synthesis separately, separately, assembler separately. I don't want to do them separately. I want to do everything at a stretch. When you say, then we have a shortcut known as compile design. You can see there is a play button. When you click this start compilation, automatically it does all the steps for us. It performs analysis and synthesis. It performs filter, which is placement and routing. It also generates the programming file. All these information are available for us right now, where we don't want to perform them step by step. All right, so once this is done, how do we program the device is the question now. So we should go to tools, and then you can see here programmer. So tools, then programmer, if you click here, and you can see the programmer. As I mentioned, you can see inside the output files directory, you can see logic underscore gate.sof file. SOF stands for SRAM object file. So this object file is targeted for this device, which is our Max 10 device, and it is ready for configuration. I have just connected the JTAG, where you can just say that this is USB blaster, which is USB 0. It is ready for programming the device. So the moment I say start here, I should get in the progress 100% successful. If it is failed, then I have to hit it once again. Okay. Once I say start, it should show 100% successful. That means I can modify the switches SW0 and SW1, and I can check the output. That means the LED R0 is glowing or not. I can try it out. Let us try that right now. So say start, and it shows that 100% successful. Now, what is the meaning? I can modify SW0 and SW1 and see whether LED R0 is glowing or not. This is what is the traditional method which we follow. Right? Now, when you have the board with us, that is called as the live hardware, in which we need to perform the operation like that. If that is not the case, we are going to perform the operation in terms of the virtual labs with the remote console, where I am going to show the demo with the help of the virtual lab, where I am going to show you the lab manual first, and I will give you the details what are given in the lab manual, and how are we going to progress with that lab. I will explain you step by step along with the conceptual explanation. So once this is done, we can close this window so that you can It ensures that you have programmed the FPGA. If you want to close the Quartus Prime design software, yes, you can close it. Or you wanted to close this project, you can just say file close project. It will again come back to the same thing. Right. Now, what is the that need to be addressed here? Let us explore them one by one. Now we know what is synthesis, what is fitter, I explained you. And now we can see that once you perform the fitter operation like plan, early place, then route and finalize. Each and every place what is happening we can see here. Plan, it performs IO placement and routing and clock resource selection. In the early place, it performs early assignment of core logic to device resources, and then you can perform placement. And when we do routing, it gives the information related to logic elements, registers, DSP, RAM, all are interconnected. They are routed, and then we can perform post-routing optimizations here. These are the steps. Now, this slide is very important for you to understand because I did the logics in two ways. One, I did start analysis and elaboration separately, start analysis and synthesis separately, start fitter separately. And I also explained that all these three steps can be combined together, and we call that step as compilation. You can see that start compilation, that is full. It performs all the three, but I wanted to do them step by step. When you say, you can do that step by step, like start, analysis, and elaboration. What is the process? It takes the syntax and builds the hierarchy, and it performs the initial synthesis. And the start, analysis, and synthesis, when you say, it synthesizes and optimizes the code. When we say start fitter, it performs placement and routing and generates the output netlist. So these are the steps which we need to understand. Either we can do all the steps at a stretch, because when the design is very small, we don't want to do them one by one. You wanted to do everything at a stretch. Yes, that's a good idea. When the design becomes quite complex, it is always better to do them step by step. So in that case, yes, first you do analysis and elaboration, then you perform synthesis and see what happens. Then we can go to the fitter operation. Right. So what are the weavers we have seen? RTL weaver, technology map weaver, and then what I'm going to show you later would be the state machine weaver and the chip planner. Okay. So after going through the labs with virtual console, I will show you two quick demos on, one is on the state machine weaver and the other one is on the chip planner. Okay. Now let us explore how we can access the board virtually. Right, and then we will come back to these two. Now you know what is RTL weaver, which is technology independent, and the technology map weaver, which we do it after synthesis and then also after placement and routing. What are the two important things we need to go through is what is the state machine weaver and what is the chip planner. Right, so let me walk you through the next lab. Right, what is the importance of that lab? First, let us understand, and how that hands-on will helpful for us. Let us explore that. So this is the folder which would be shared with you. And what we are going to do in this lab, I will explain that in detail. You don't require the board for this lab. We wanted only the Quartus Prime design software, and you need to install the Cyclone 5 library, which is required for this. If you have installed only Max 10, I request you to install the Cyclone 5 library also, because we have enough time. You are going to do the hands-on lab till the evening. You can try that. So what is the objective of this lab? Is we are going to perform all the steps like what we did in the earlier program. We are going to perform the analysis and elaboration process. We do pin planning. We are going to do synthesis. We are going to do implementation. We are going to generate the programming file, everything. But only difference is we don't have the board available with us. So since we don't have the board availability, we are going to follow the virtual labs with the remote console setup. I will walk you through this lab. I will do all the steps and show you a demo, and also tell you how to upload our SRAM object file with the virtual labs. Then I request everyone to follow the same steps, and then you can complete the lab successfully. I'm going to do lab 1. You can do lab 2 and lab 3 as exercise later. Let us start with this lab. The first few pages of this lab is going to help you to understand about the tool installation. Since we already installed the tool, there is no need in going through that pages. If someone has not installed, I request you to go through these pages where it explains that you wanted the like addition software, which is the Quartus Prime. And for this lab specifically, we wanted only the Cyclone 5 device support, and you don't require the Max 10 FPGA device support. Okay. Right. So you require only the lab manual. You don't require anything other than this lab manual. Okay. Right. I will put this lab manual in the share, and I request everyone to go through the steps what is given in the lab manual. Before that, I will show the demo completely what is happening in the design. Let us start with the Quartus Prime design software. You need to click New Project Wizard. Okay. I will share the lab manual after I show the demo, right? So that you can do that in the hands-on, and you can come to know that what kind of problems you face, right? If you are trying to do parallelly, there are issues that you cannot catch up the details. You can note down all the points. I will share that after the demo in the shared folder. I request you to start immediately, and I will be available online to help you out. Okay, let us start with the new project wizard. And please ensure that what are the important bullets that need to be discussed in this particular lab manual. I'll explain. Name of the project, right? Verilog file should be switched to LED. So don't give any other name, because the module name of the Verilog, which is given in this lab manual, is switched to LED. Follow the same project. The top level entity should be switched to LED, and that should be case sensitive. You can create any project name, any directory, but then the name of the project should be switched to LED only. Okay, this is first point. Second point, what we should remember, this particular lab is targeted for the Cyclone 5 device, where the family of the Cyclone 5 device, the family filter is given here, 5C SE. That means it is Cyclone 5 device, that's called 5C. And you can able to see that the information of the family filter is provided in the lab manual itself. You can copy that. Okay, so these two steps let us do first, and then I will show the remaining steps one by one. Right, first click the new project wizard. Okay, click next, and now you can have any directory name. For example, I say test, and then I say remote lab 1, something like that. So this working directory can be anything. But what is the name of the project should be switch_2_LED. Don't forget that. Working directory can be anything, as you wish, whichever name you want to provide. I have just given here test remote lab 1. And what is the name of the project? I gave switch to LED. What is the meaning is whichever switch I am changing, corresponding LED should glow. Is it glowing or not? That's what we are going to check now. Okay, say next. And please ensure that you select Cyclone 5 instead of Max 10 for this example, and copy the family filter from here and paste that in the Quartus Prime design. Okay, after you paste it, you select corresponding device, say next, nothing to do with the EDA tool settings. Say next and say finish. Okay. Now, what is our next step? Go to File, New, Verilog HDL. No change. But you don't need to write the Verilog code. The Verilog code is already available in the lab manual. Okay, so you can directly crawl and then get the Verilog code from the lab manual itself. Where is it available? I'll show you. This is the switch to LED program, and the Verilog file is available here itself. You can see. Okay, so don't copy from here. Copy from this hyperlink. Okay, you click this switch to LED.py. This will take to our GitHub site. Okay, and I will show you where the entire details are available. You can try. Okay, so this is our workshop, Introduction to D1 SOC Labs Land. Okay, this is our GitHub site. I will share that link with you, and I request you to go through that in detail. Okay, first let us copy the Verilog code from here. And you go to the Quartus Prime Design software and paste it. What is the meaning of this code is there are 10 switches. There are 10 LEDs. Whichever switch we are changing, corresponding LED is glowing or not. That's what we are writing. Assign LED R equal to SW. Okay, now save this file. So file, save as, and say switch to LED.v, and just perform analysis and elaboration. Okay. Now, once it is performed analysis and elaboration, it shows 100%. What is important for us is to do pin planning. How did we do pin planning for the earlier program? When you say there were only 2 switches and then 1 LED. Therefore, it is easy for us to go through the specific FPGA and then we can do pin planning. Right now, what is the problem is this code requires 10 switches and 10 LEDs. So you have to perform pin planning for all the 10 switches and 10 LEDs. See here, there are 10 switches, and for all the 10 switches, the pin number is provided, right? LEDs, as well as for the 10 switches, you can see here, as well as for LEDs. It is very tough for us to do this manually. Why? Because in the earlier example, there are only 2 switches and 1 LED. See, we looked into the manual and then we did it. Now also we can refer into the lab manual and then we can still do it. There is nothing wrong. Okay, we can still do that. For example, if I open the specific content here, okay, let me close this and then open a tab here. DE1 SOC lab manual. So this is what we want for this particular lab. Okay, which is an SOC which has both FPGA and an ARM Cortex processor. Both are available. So let me open it and show it to you, and then I will go to the presentation once again. Give me a minute. Okay, now if you open that manual, you can see this is the D1 SOC, which has 10 switches, 10 LEDs, everything is there. Same like your D10 light bulb. You have switches, you have LEDs, and then you also have the hexadecimal display. But now, what is the difference? Let us see that. The difference is if you go through the pin constraints here. All the switches you can see, there are 10 switches and then there are 10 LEDs. We have to enter them one by one. Okay, it is definitely tedious and very tough task. Why? Because if you go to assignments and then when we do pin planner, you have to do pin planning for all the 10 switches and also for the 10 LEDs, which is tedious and time consuming, number one. Second thing is definitely there are chances of error prone. You will definitely make some mistakes. How do we solve this problem is, we are going to perform a tickle control. So the pin planning need to be done automatically with the help of a tickle console window. How do we do that? I will show that, understand, and then while performing the hands-on, you can definitely do that. So I click D1 SOC pins.tcl file, which you can click. It will automatically take you to our GitHub site where you have the pin planning for all the switches and LEDs available. Okay, other than clock, you copy everything because this code is a purely combinatorial code. There is no need of clock here. You just copy all the 20 commands. All pin numbers are already available here. Come to the Quartus Prime Design software. Remember, go to View, Utility Windows, Tickle Console. View, Utility Windows, Tickle Console. When you click, the Tickle Console will be opened. And you can paste all the commands and say enter. When we do this, and then you open the pin planner, all the pins would be automatically done. We don't want to do them one by one. This is the advantage of the tickle script, where you can use that for pin planning, number one. We will also use that for timing constraints in detail tomorrow. Okay, so now what we have done, we don't need to do pin planning automatically, means we don't want to do that manually. We did it automatically. Just pasted all the commands and it has done the pin planning absolutely well. Okay, now what is important is we have to compile the code. Okay, so compilation, you are aware, just click the play button, do compilation. Now there are two more steps. After compilation, we have to implement the design onto the board. To implement the design onto the board, there are two challenges here. One, we don't have the board, right? And then we cannot connect. Now here, what are the two steps? One, we need to create a login for our remote lab setup. That's the first step. After we create the credentials, the username and password, we can access the board remotely and we can upload our SRAM object file. That's what we are going to do in this lab. How to create a login and what are the links that are required. Everything is available in the lab manual only. You don't need to search anywhere. All the informations are available. I request you to go through that and then do it. Okay, I will show the steps again so that it is easy for you to practice on your own. Right, now it shows 100%. What we are supposed to do here, we need to perform the FPGA programming operation. How do we do that? Here, we are going to use setup called as the labs land setup. What is that setup? I will explain that quickly now with 2-3 slides. Then we will come back and I show you how that helps you to perform virtual lab setup. So I'll minimize these informations. Let us go to the labs land presentation. So what is the traditional logic when you say we create the design, We apply constraints, we compile the design, we do close gaming. So this is for tomorrow's session. Directly we are compiling and we are configuring the design onto the board. But now what is important for us is all these steps when we do, what is very important for us is to implement the design onto the board. We did pin planning, we did compilation. What is the last step when you say we have to program your FPGA? This is what I showed you. Right? But then what is not possible, as when you say we cannot do that in the live hardware. But what we are going to do now is like we are going to do that with the labs. What is this Labsland setup when you say? Labsland is a company who have the setup of the real laboratories. They connect schools and universities with real laboratories available somewhere else on the internet. They are real laboratories, but not simulations. And the laboratories are physically there, and the students from these schools and universities system. It is a fee-based model for them, but then there is no charge for us today. That means at the end of this, till the end of this course, you can use this Labsland without any problem, right? Because this login would be temporary, and they can delete this login at any point. So what I suggest you is you generate the SRAM object file, and you can implement the design onto the board, and we can check it whether the functionality is perfect or not. How do we test that? I'm going to show you right now. Okay. For doing that, I need to show you one more slide. There are two ways to check with Labsland. One is called as an IDE mode. The other one is called as a no IDE mode. And what we are going to see in today's lab is no IDE mode. What is the difference between IDE mode and non-IDE mode or no IDE mode is? If it is an IDE mode, we don't want anything to be installed in our system. All the compiles are directly happening on the cloud. But the problem is, since we don't have the system and what kind of IP capabilities and what kind of integration can be done, right? There are limitations. What is the other one which we are going to use it for today's lab is called no IDE mode. What is the advantage of this when you say we have the software installed locally in our laptop and we are going to access this Labsland FPGA remotely. This is what we are going to do in today's lab. So that will give you a clear picture how to connect to the Labsland. Okay, now we will go back to the lab manual again. Click here. So you can see Labsland is a company specializes in hosting remote labs. So click on this link and you will be instructed to create a student account. So you just click this link. Hello. For example, if you are creating a student account for the first time, you should click here, create a student account. If you click this will ask you to create an username, a password, and you need to confirm the password, then you should sign. You can do within 2 minutes. But if you already have a login, for example, after this, you already have a login, you can click this and you can enter your username and password. Okay, first login as a student means you create a student login and you provide your username and password and confirm the password. Then you can log into our Labsland setup. Just give the username. I'm giving my username followed by the password. The moment I click sign in, it will take me to the Intel D1 SoC. Right? Here you should say access this lab. And again click access. Okay. The moment you click access, it is reserving for you. The board will be reserved for you. It shows that you are next, and then it is going to open a screen where you can see the FPGA. Right? And this will be available for only 3 minutes. Within this 3 minutes, you have to upload your SRAM object file and you should verify the output. What is the name of our project? Let us see that. Test Remote Lab 1. Okay, so what we should do is like you have to choose the file here. On the right hand side, you can see choose file and go to the C drive and say test remote lab 1, right? This is our project name. Inside the output files folder, select switch to led.sof file and say upload. Now you can see there are 10 switches. As per our program, whichever switch we are changing, the corresponding LED is glowing or not, we should check. So click now. Definitely, I am going to share it. Don't worry, and I am going to also share the link with you where you can download the PDF document directly. Okay. The objective of today's lab is that everyone should be comfortable in accessing the remote lab. Okay, right. Now the question is, if I have completed before 3 minutes, okay, what you can do is you can click here, leave now. And please don't log out. Because once you log out, again, getting the board will be a tough task for you. Because you can see that there would be a limited access. It is only for 3 minutes. Okay. Once you log in, you can log out once you complete the lab. Or for example, you can also see that I have 2 SRAM object files ready right now. Then what you can do is you can implement 2 designs, then you log out. So don't log out and then again log in and try for the second design. Okay, so I wanted to continue the second design. What you should do is you should click access here and say redirecting. Again, you go back and then continue. Here, if it is your own program, then you should select this. But there are some ready-made programs that are available here. Blinking LED, mirroring switches, clock programming, everything is already available here. This also you can use. Okay, I wanted to try another example. You can say choose file. And you can choose anything, whatever you want. For example, inside the downloads folder, I have a labs land setup, right? Something like labs land. I have another file. Okay, I just say open and say upload. Now you can see this is a clock divider example. Okay. So once you complete, then you say leave. When all the steps are completed, then you log. Don't log out before that. Okay, you want to try one more example? Just again click access. Try one more example, then finally you log out. Okay, so if you go through the lab manual, you can see there are 2 links. One link is for creating, another link is for accessing. You click this link, it will ask you to go into the no IDE mode. You can see that. Okay, so totally there are only 3 minutes. In that, effective minutes are only 2 minutes for you. Okay, within that 2 minutes, you have to upload and then ensure that your SRAM object file is 100% completed, because the last 1 minute you can verify your functionality. This is the way how you can see the Lapsland laboratory and you can upload the SRAM object file. The example what I have shown right now is the first example. There is one more example called 2:1 multiplexer, and the other one is the Night Rider file, which I showed you some time back, which is a clock divider example. I request you to try all of them. But it is very essential that you create a login with a LabsLAN setup. And another important thing is you should have the Intel Quartus Prime design software installed along with the Cyclone file libraries. Those two are important. Okay. Right. Now, what is critical and important for us is like, where do we check this? I will show both. One. So if you click this link, it automatically takes you the tickle file, everything, right? So where are these files? Okay. I will show that information to you. So this is our dev cloud, where you can go to the FPGA dev cloud, this place, right? Where you can have the information related to all our logic. So let me walk you through that. Okay, so let us go to the quick start guide, where you can see the workshop, which is the intro to the D1 SoC LabsLAN setup, where you have the file here. This is the lab. This is the intro lab remote board labslan.pdf file that is there, which you could download from here. Okay, so I'll share this GitHub file with you in the chat. I request you to try that. Also, I will share this manual with you. I'll stop sharing and I'll put that in the chat. Just click that link, go to D1 SoC LabsLAN, download the intro lab remote board labslan.pdf file. Once you download, you can continue and do the lab which I provided in the LabsLAN set. All right, I'll start sharing my screen again. Right, so once we do this, what is important for us is we can verify the functionality by using the LabsLAN. There are two more things before we conclude this session. One, I wanted to show you the chip planner, and the other one is I need to show you about the FSM, the state machine viewer. Let me walk you through two examples, and then we can understand that how that could also be possible. Go to File, Close Project. What is chip planner? Let us open that. We will open the memory file, which we opened sometime later, right? Sometime before, where we verified about the single port memory. Let us perform compilation of that design. Okay, so now if you go to Tools and you go to Chip Planner, okay, you can see the FPGA layout. You don't need the files because the files are already available in the lab manual itself. Okay, and if you wanted to download the files, you download from the same GitHub link which is given to you. In that only, along with the PDF, you download the remaining. But if you download only the PDF lab manual, that is sufficient because it has everything. Okay, in the lab manual itself, if you click .v file, Verilog code will be opened. If you click the .tcl file, TCL file will be opened. You don't need to download them separately. And you can see this is the link which I gave you in the chat. Let me stop sharing. See, this is the link which I gave you, right? So this is the link which I gave you, right? In the chat. If you go to this link, you can click the introduction to remote labsland.pdf. And once you open that, on the right hand side, you can see download. You can download. Are you getting my point now? Once you download, this PDF itself will have a Verilog file, .v file. Everything is there. There is a chat window. There only I have shared it. Are you not able to see my link, what I shared? Okay. So then I will put that in the Google Drive, in the share. From there, you can take it. Okay. Just give me 2 minutes. I will put the entire information in the Google Drive. Then you can take. Okay, so there must, yeah, there may be a mistake probably then. Till now it has been shared to only panelists probably. I can try that. Now can everyone please check whether you are able to see the link? Okay, good, very good. Now I will share it once again. Now you please open it. So now once you click the link, it will take you to this page, right? And from that page you can download. So this would be the page where you would be seeing. Okay. And in this page, you click here, Introduction to Remote Labsland PDF. Just click that. And on the right hand side, you can see download and continue the lab. Is that, can anyone confirm it whether you are able to go to that page and then download it? Yeah, so then thanks for confirming. Let us continue the lab. So over to organizers. If you wanted to stop sharing, you can stop recording, and we can continue with the hands-on lab.
Okay, sir.
Yeah, you can stop recording of the session, and then I will be available online. And if the candidates have any doubts in the hands-on session, they can raise request, and then if required, I can show demo to them.
Okay, sir.
Right. Right. Can anyone confirm that we are able to go through the lab manual and you are able to create the login with LabsLAN setup? Can anyone confirm in the chat? Okay, good. Okay, so what I will also do, I will make a copy of that in the Google Drive, right? I will copy that entire folder in the Google Drive, and I request the professor to share it. Then you can go through that also if you have any issues with the link, okay? All right, so please try that. Please try to complete that. Right, I will share that in Google. Can you install the software and please try the simulation lab without the DET and light board, means you write a test bench and check. And also you try this LabsLAN setup remote console also. Okay, you have the files with you, but please ensure that you complete it today. You can access the virtual lab in LabsLAN setup for next few days. Okay, so I cannot guarantee whether you will get all the 7 days and something like that. But then we have requested them that you can use it for a few days. That is definitely possible, right? If they remove the link and then you create one more and then use it for some more days. Is that okay? It won't be chargeable for a few days, no problem. Okay, good. You try this, and that would be a good idea for you to understand about the LabsLAN. And one more thing is the lab files are also shared in the Google Drive. You can access it. It has the folder where you have the lab manual plus the lab files. All are available. If you want any other information, please let me know. I will be available in the chat only, right? It is available in the Google Drive. Inside the lab one, there is a hands-on session, day one hands-on. Probably inside that it should be there. I will locate where I have put it. Yeah, inside the course materials, day one, inside the hands-on, there is a folder. Okay, there is a question that, right, so now inside the day one, there is a hands-on. Inside the hands-on, you see, is there anything inside? Okay. Or you can just try once again, just come out and then try login. You will come to. Okay, so you got the output for the second one. That is great. What is the problem with RAR file? So please try that once again. Okay, so there would be a components folder. I will share once again and show you. Okay. Inside the tool, right, installation directory, you can also see, for example, inside my C drive, I have the Quartus Lite. So this is my 18.1. Inside this, you can see there is a components file. If you open that components file, you can see there is a Quartus Lite setup, windows.exe file. You can double click this exe file and then also you can start the Quartus Prime Design software. Inside this, you can see that what are the 2DZ files. You can see this is for the Max 10 and this is for the Cyclone file. Since we have installed that as a package like 5.8 GB, you don't need to install this 2DZ file separately. But then if you have installed it separately, then I request you to install Max 10 and Cyclone 5 because these are the two we are going to use for our lab. Can you please show once again how to select multiple pin in pin planner? Multiple pin in pin planner. Okay, can anyone tell me what is that? It is showing only for faculty, not for students. What is that? Can you please elaborate on that? I couldn't understand that. Which is showing only for faculty? Are you telling about the Lapsland link? Okay, Lapsland account, see, when you create it, okay, see, if you have any, you click the link, I will tell you how exactly you can try that. So don't try multiple things, just try to do only one specific information. When you click link, so I'll just share, okay. I will share my screen. You click this link, hello, and see, you have to go to the student account. For example, see, I will log out. Okay, so don't go here. Log in as an instructor. Don't go to this place. Okay. The moment you click this link, you click here, create student account, and create a username, create a password. You confirm the password, sign up. After that, you go already have an account. Don't go to the instructor account. Are you an instructor and all? Don't say. Go only to this page. Sign up as a student. When you click first link, go to this page. If it is coming something wrong, just close it again, open it. You should get this page. Sign up as a student for the Intel hardware. Create a username, create a password, confirm the password, and then sign. Try and let me know. Still have issues because 2-3 people have completed the lab. Okay, definitely you should also get it. Okay, so there was a question on the pin planner. Okay, so what is important is, see, when we do pin planning, we don't want to do it step by step. So what I told is, you click this D1 SOC pins.tcl and you copy all the pins. Okay, and copy this, go to the Quartus Prime Design software, go to the view, utility windows, tickle console. Okay, and then in the tickle console, you paste them. First it is you clear them, then you paste. After pasting them, press enter. Automatically all the pins will be taken. Are you getting my point? If there is any doubt, let me know. Okay, please put that in the chat. If there is any issue, I will help you out. You're welcome. Okay, so let me know, please. Anything required, let me know. It is okay to have the 21.1 version, no problem. Just try one example with LabSLAN. Okay, if that works, then you can continue. Or see, the other examples will definitely work. Does not have an issue. Okay, try one LabSLAN example with 21.1 version and connecting to the board. If that works, you continue, no problem. There is nothing to do with version here. Only thing is, some of the labs are done with 18.0 and 18.1. Due to compatibility issue, what we thought is it is better to go ahead everyone with the same version. Right, because it is very tough to rectify all the problems in online. That's what we thought we can have the standard version. Let me answer about this question. Okay, so there was a question on the mapping. Okay, I will explain. See, when you have a design, right? When I do that with RTL Weaver, the RTL Weaver is showing you that this is the RTL schematic. It does not show which RAM it is using. It is showing that the memory is used by this code. Okay. But when we do synthesis, for example, when we perform analysis and synthesis, it showed that it is using memory bits. You can see that it is using 512 memory bits. This is for mapping. So what happens is, if you see technology map viewer, which is post mapping, this is after synthesis. After synthesis, you can see that which one is used. Okay, you can see there is a block memory. But during synthesis, okay, you can see that how many are used. For example, I will just rerun this. I will say start again. Okay. Let us go through that. When we do synthesis process, definitely there would be a difference between synthesis and implementation, because in synthesis, you don't have the interconnect delay. You don't have the accurate interconnect delay. You will have only the estimated delay, because when you need to interconnect the components, definitely you should require the wire delay. Only when you perform placement and routing, you can have the exact wire delay. Okay, that is one. Second thing is, during synthesis, that means your normal mapping operation, it shows that how many bits are used. It doesn't show that out of the resources which are present in FPGA, how many are used. That information won't be captured during synthesis. Okay, when you expand this analysis and synthesis and you go to the resource usage summary, you can see how many are used, but you cannot see how many are present in that, how many are used. Okay, that's what we are trying to do. In the RAM also, it shows that which RAM is used. You can see single port RAM, but doesn't show that how many memory resources are available in that, how many are used. That's what we try to do fitter. When we do fitter placement and routing, what happens is, you will come to know that how many resources are present inside the FPGA, in that how many are used. Another important information is there may be a change in the area also, because while performing placement and routing, it can perform some optimization. There are chances in area improvement or reduction or whatever. Now you can see there is a difference. And you can also see there is a difference in the schematic. Netlist viewers, if you go to the technology map viewer post fitting, you can see that there is a memory. Okay. And if you expand this fitter, and if you go to the resource section and see resource usage summary, you can see how many are present and how many are used. Right? Hope I could be able to answer your question, right? The role of technology map viewer. Are you very clear now? Okay, thank you. Right. I was able to do the first lab. Good. So it is not like only the first lab, you can do everything. But the basic idea is like, I wanted everyone to be aware of how to do basic digital system. That's all, basic design. Second thing is, after generating the programming file, how do we take it to the labs LAN setup, that is virtual lab. These are the two important goals which we are trying to do in this. If someone is using the different version, please try one labs LAN example. Okay. What is the problem? Why you cannot create a Lapsland account? What it shows? Okay, so right, so right, let me, okay. You can try after some time then. For example, what exactly it shows to you? I should understand that when you click that, right? I will share my screen. When you click this link, it takes you to the place where you have to create a student account. Am I right? You click student account, create username, create the password, and then you confirm the password and say sign up. If it is not allowing you, you can wait for some time, because if multiple people are trying to log in, there may be chances that if not, don't try to create a login with instructor. It should be on the top, sign up as a student of the Intel Udemy. Okay, so I will put that link again in the chat, so you can try that, no problem. You try the link, okay? Yeah, try after some time. Okay, so if not, then try after some time, because there are only minimum set of boards available. Everyone cannot try at the same time. So what you can do is let the people who are working, let them log out. You can try that once again. Meanwhile, you can develop the lab for the second one. Generate the SRAM object file. Once the second lab is ready, then you can try that, because you wanted all the SRAM object files ready, then you can log into it. Okay, good then, fine. Thank you. Create it, no problem. So it will take, see, the main idea is everyone should have a login, and then you should ensure that you get an idea of how that could be implemented in the remote setup. Definitely it will work, okay? Okay, I'm showing you about the FSM. Okay, finite state machine, which is a state machine weaver. I'm creating a new project here, see, and say FSM weaver. Okay, and what is the name of the project? I just say FSM. That's the name. Okay, create it, empty project, say next, and select max 10. Okay, so now what we are going to do is file new Verilog HDL. So in the drive, I already have where which has the Verilog code and the test bench for a finite state machine. I'll just take that. I have a .v file, and I change this to FSM. So file, save as FSM.v. Similarly, I need to create a test bench. So file, new, I have a Verilog HDL file, and then I have a test bench. Listen carefully. So this has a test bench. FSM underscore TV, let it be like that. And the design name, you change that to FSM. Now you save as FSM underscore TV dot. Okay, now let us do analysis and elaboration. Fine. Now we wanted to do the test bench. Now go to assignment settings, select the model sim algebra, select compile test bench, test benches, new FSM underscore TB, add FSM TB.v, add, then you say OK, OK, apply, then OK. Right, so once we do this, you can perform run simulation. Now you can see this is an FSM finite state machine. Okay, so now you can see. Now if you minimize, you can see that. Right, whenever you get 1101, so you can see that the output is high. But how do you wanted to see that FSM in the Quartus Prime design software? That we will try now. Okay. Now, if you go to tools and if you go to netlist weavers, particle weaver I showed you earlier, technology map weaver, technology map weaver post fitting. Now you can see state machine weaver. Now you can see the state machine. Got nothing, got one, got one, got one. You can see the FSM. So this is the capability of the Quartus Prime design software, which is called as the state machine. What you can also see is go to tools, and then you can also go to chip planner, where you can see the resources in the chip. What resources are used that you can see, whichever resources are used that you can see. Do you have any other doubts? Okay, so your test bench file also would be same only, right? Same. How do you create a project? Same. You write a file, new, create a file, and then you copy the test bench. That's all. So fsm.v is a separate file. FSM testbench.v is a separate file. Just say file new. You create two files. One file for the design code and one file for the test. Okay. I will share this code with you in the drive. You can check the FSM state viewer now. Okay. Is it clear? Okay. I'll put that in the drive now. I will put the Verilog code as well as the test bench for the FSM. Try whether you can able to see the state machine or not. There you can see the state machine viewer. In the earlier examples, we have seen RTL viewer, then technology map viewer post mapping, then post fitting. In this example, we can also see the state machine viewer. Yeah, Biplav, you can share the drive link to everyone so that they can access the files, right? Can you please help in that?
Sir, it has been already shared with all the participants in the registration confirmation mail. But I will also share it in the chat box so that they can copy it.
Sure, sure. Excellent. Good.
Dear participants, the drive link has been shared in the chat box. You can find it here. Also, we have shared the same in the Telegram group.
Okay, so there may be a problem, right? So what I'm telling is, see, what was explained in the 17th page, I will explain it to you once again. See, in the first two examples, it is a pure combinational logic. But in the tickle file, you have 21 commands. By mistake, if you copy the last command also, means the 21st line also, if you copy, nothing will happen. Because there is no clock pin for that. Okay. By mistake, if you would have copied, then nothing will happen for the first two labs. But switch the LED and the multiplexer does not require the clock signal. Whereas for the last lab, you require the clock signal, which is the Night Rider lab. Okay. So for the last lab, it is very critical and important that the 21st line in the tickle file should also be copied, because in there is a clock signal, and DE10 light uses a 50 megahertz clock, as well as the D1 SoC uses a 50 megahertz clock. You can see the clock should be connected to the pin AF14, which is 50 megahertz. When you copy paste, there should not be any question marks in the port direction icon. Okay, so in the first two examples, by mistake, if you would have copy pasted the pin planning, then also there won't be any problem. You can see a question mark. But that question mark will be removed in the third lab. That is what is explained in this manual. Is that clear? Okay, after opening the pin planner, what you need to do is directly go to the link, copy the pin planner commands, and paste it in the window. How do we paste it? I will show it again. You go to View, Utility window, go to Tickle console, and you have to paste it. So you can see that the Tickle console will open. Here you have to paste all the commands. After pasting, press Enter. That's all. Is that clear? You try one example for pin planner, then you will automatically come to. Okay. Because in the first example we did for AND gate, only 3 pins are there. But for this example, we have to do it for 10 plus 10. So LED 10 and then switches 10. Definitely. The lab manual is complete. There is nothing you need to worry. Okay. So the lab manual has all the information. Step by step you follow. You do the first lab, you will get an idea. Because in the second lab, we are going to use the same pin planning. For the third lab, only one pin we are going to add, which is a clock pin. Other things are same. The lab manual is complete. Nothing you need to worry. Correct. Copy that. Copy everything along with the entire manual. Yes, entire things. All the 20 pins you copy. 20 plus 1, 21. Those who have completed the at least first lab of the remote console labs land can try the FSM lab. I have shared that in the drive. The Verilog code of the FSM and the test bench is also available. Please create a new project to perform functional simulation, and also after performing compilation, see whether you are able to see the state machine viewer. Don't worry about the waveform that is taken in terms of simulation. Okay, so don't worry about that. Okay? You can just understand what is happening in the Night Rider and how the sequence works for you when you take it to the labs Lancet. Okay, then you can see that how it works out. Don't worry about the graph. Okay, the graph is just showing a simulation logic for you. In the FSM itself, so right. So whenever you have the FSM, right, you can also see at what condition it transits from one state to another state. That would be available. Source state, destination state, at what condition it is working, and what kind of encoding it follows is also. All this information, sir. Just try that with multiple examples. You will come to know that what kind of transitions is that and what kind of encoding. I will see last lab. There are two important errors. Okay, you cannot get the correct output. Why? Because there are two important informations which you should note down. In the nightrider.v code, when you open it, you can see there is a clock divider code, because we don't want that to work at 50 megahertz, right? 50 megahertz, we are dividing that into 1 hertz. But there are two places there is a mistake here. Okay. One is, you can see here always at passage of fast clock is there. And then you have the one place it is having slow clock is there. When you directly copy paste this code and then you take it to the LabsLand setup, the output may not be as expected. Okay. So it should be like you have to reduce that and then see the output like 50 megahertz like that. Okay. So that kind of things are not happening, may not happen because there is a bug in the code. What is the clue? Yes, you have to see here the clock divider count. You can see 2 double star counter size -1 is there. Now the counter size is what? 5 is there. Now you can also see always at passage of clock. So these two clues are there. This you have to think and modify the code. Only then it will work like as expected. Please think that, okay? Otherwise it will be a problem. Okay, let me explain. Let's see here. Code given intentionally has errors. See if you can find them all. Okay, so please try that. Only then you will get an output where it can work properly. It should go like this and then it should come like that. That may not be the case when you do that. Okay, because what is the problem? I'll tell you two things. One is the board is 50 megahertz clock. So we need to reduce that using the clock divider. So where you should say 2 power n. We wanted to reduce that into 1 hertz. But what is written in the code, whether it is reducing from 50 megahertz to 1 hertz or not, you just check, do the calculation. If that is not the case, you have to do it. So your lab instructor goofed and did not calculate the right divide ratio from 50 megahertz to 10 hertz or 1 hertz. So you try that. If only that you modify, then you can. Okay, so the easiest way is the counter size looks good when set to 23 or 24. So see the counter underscore size, what was given in the code, and please modify it to the suggested value, what is given. Okay, in this case, the counter size, if you see, right, the counter underscore size is 5. That's the problem. Modify the code. If you modify the code according to that, then automatically you can see the night reader. Check that whether it is working. After completing the third one, I requested you to do the FSM lab. Please do the finite state machine lab. The FSM code and the test bench is shared with you in the Google Drive. Please copy that and perform simulation and check whether it works as per the pattern. Then you perform synthesis, implementation, and you open the FSM state machine viewer. Can you do that? For the finite state machine lab, you don't need to do pin planning. Okay. What I wanted you to learn is like you have the FSM code. Okay. You have to understand whether it is a melee machine or Muri machine, that you can get the details, because you can see there are two always blocks and you can see the present state as well as the input that is there. And also you can see there is a test bench. What I wanted you to do is you perform functional simulation first by copying the test bench and then check the simulation. And after you compile the code, you have to see all the four: RTL Weaver, technology map Weaver post mapping, technology map Weaver post fitting, and you also go through the state machine Weaver, where you can see the source state, destination state, and condition, the transitions, and the encoding. All these information are go through this and get an idea like how you can also weave the state machine. Because in the earlier cases, we have seen only these three. But in this lab, we are seeing the state machine, because the earlier labs are not FSMs. But this lab is meant for state machine. That's what I gave this. So go through the state machine Weaver and also click the chip planner to see that, okay, what resources are taken by the planner, that you can see that. How many logic array blocks are taking, all those information you can see that, which is the coordinate and which is that LAB, that information you can see that. So this is the logic array block. It is the present state and next state that is used. You can see that in the planner. Okay, so do that. That will give an idea of going through all the reports. All right, so I will share my screen and then show you one more remote lab setup what we have. Okay. Let me explain that to you. Just get an idea of like what is the other kind of remote lab setup which could be possible. For example, in your institution, you can have the boards that can be installed in the server. Okay. And now what you can do is you can get the access password. You can get the IP address and the password, and then you can still access the board by sitting in your home itself. So there is one more setup that what we have. Now, what is the setup we have seen now? Is the first setup in the morning is you have to connect the board physically. The second one, what I showed you, is through the labs LAN setup. The third one, what we can also try is that you have to host all the boards in the server in the institution. Now what you can get the IP address and password from the institution, and you can access the board. Okay, so how do we do that? Okay, so I will just show that. With the examples I will show you how visually you can see that. If you go to the dev kits, okay, this is our GitHub site which I shared with you. There we have DE10 Lite, because I have connected my board with the DE10 Lite that we can try now. Inside the DE10 Lite, you can see that example projects. Okay, I will just open that. And I have multiple examples like OR-gate, parity, like that. I will show you 2 examples and then I will show you nitrate. 3 examples we will do. The first one, I will take the OR-gate now. So if you see, there is an OR-gate dot QAR, stands for Quartus archive file. You have to unarchive that file. Okay, and then you will have the entire folder ready. Click that file, and then you have to download it. Okay, I have the Quartus archive file here. Now what you need to do is you need to open the Quartus Prime design software, and then you can say open project, go to downloads, click the orgate.qar file and unarchive that file. Okay. Now what you can do, go to the files and you can see there is just the OR-gate file. You have assigned y equal to ARB is there. Just perform compilation. So meanwhile, I will show you that what you can get an idea here. So let us go through that now. So if you go through the dev kits and you select that, okay. Okay, here you can see the remote console guide. So here you can see that how to set up that, and there is a system administrator page where you can set up the development kit, okay, with a VPN. This could be done in your institution, okay. And once this is ready, you can get the username and password. You can get the IP address and password. After you get the IP address and the password, you can upload the SRAM object file and you can see the board on the screen. This is another method. the institutions can also host the boards in the server and students can also access that. Right? How that could be possible, that I will show you a demo now. And the instructions are available in this page where we will help you out to host that also. Okay. So let me show an example. Right now, what you can do is like you can go to the remote DE10 light. Now see here, I say start. Now you can see that. Okay. So if you are connecting the board locally, then it is local. If your board is available in your institution, then you have to provide the IP address and the password. This your institution will provide to you, right? What you need to do is select the SRAM object file and select what it is available here inside the file. Then you say link. Now this will be connected to your server. And now you can see the FPGA board on the screen. So you can see the FPGA board on the screen. Now, since it's an OR gate example, what you can do that you change the pins and you can see that which LED is glowing. This kind of remote lab setup is also available. This is for a pure combinational logic example. You can also try this for a sequential logic example, like a Night Rider example, which we did for the Night Rider example with the labs land. I can show that demo also to you right now. So let me close this project. We will again go to the same page, okay, where you have the dev kits. Right. So here you click the dev kits, go to DE10 Lite, go to the example projects, and you click here Night Rider 76. This is what is the lab which we did in the labs land. But now what is the advantage here? I will show you. Okay, so this is the labs land setup. First, let us download the Quartus archive file. Download it. Right. Now you go back to the Quartus, open project. We go to downloads, Night Rider. Then you run. Okay, so now this is my design file, which is your clock divider file. You can able to see that same clock divider, but then the size I have changed to 32. In your code, it was 4 or 5. I asked you to change that, right? If you change it, automatically that code will also work. But now let us perform compilation. So there are some more simulation setups that I will show you during the course, right? During the FDP, I will show that. There is a special session on simulation and debug. Okay, during that session, I will explain to you about the different simulation platforms what we have. Okay, now what you can do is like you select the remote and then run the script file. So go to select SOF and open the SRAM object file from here, say link. In the earlier example, we have seen that in terms of waveform, but here you can use the hexadecimal displays to see the clock debit. It is very fast, right? We cannot read it. What you can do is like you can reduce the speed also, for example. Okay, so now you can try the parameter. Now you can see this works like a clock divider. And you can also see the hexadecimal that what is the frequency. 2, 4, 8, 16, 32 divided by, you can see that. Okay, so there are multiple setups that you can definitely try. That is available in the same GitHub site. You can refer to it. Okay. Only thing is you should have the board available with you, or you should have the board available in your institution where you can get the IP address and password and you can access from your home also. Right. So there are steps available how to host the boards in the server. That information is available for the system administrator. They can definitely try that. These are the different setups which we have. Do you have any other further questions? Please let me know. I can explain to you about the fundamentals, what we have gone through the Quartus tool flow today. Because tomorrow we are going to understand about timing analysis. For example, if you go through the tool flow, I'll just share my screen. Right. So what we have done is like we have done everything today, but we didn't do the timing analysis. Since we have not performed timing analysis, you can see it shows in red. Because we applied pin constraints, but we didn't apply any timing constraints. Okay. So if you go through the Quartus flow, like what we discussed in the morning, right? Let me show that page to you to get a clear picture. So if we get into the details of that, for example, we have done synthesis and filter. We generated assembler. What step we are in process is the timing analysis. We need to do timing analysis. So we created the design file, we performed analysis and elaboration, we did return the test bench, and we performed functional simulation. We did pin planning, we did synthesis, filter, generated the programming file, implemented the design onto the board. These all steps we have done today. But what we need to apply is, we have to apply timing constraints that we have not applied. We applied only pin constraints. We will come to know how to apply timing constraints to the design, and we need to perform timing analysis. Right, then it is easy for us to move on to the system level, and once we do everything in the block level. Okay, so let us explore that. So what did we do today, right? What did we learn? That's what is important for us. There are three important concepts which we get into it today. Okay, one is we have to learn the flow for the Quartus Prime design software. That's what we did first. In order to do that, first we started with the design, like how to create a new project, and then you know how to create an open project, and then you also know how to open the recent project. There are three important things. One is we know how to complete the compilation process, and then if you have the board, directly we can go to tools, and then we can go to programmer and program the board. The moment you click programmer, automatically it will take you to the programmer page, and then we need to select the board, and then you can say start and then progress it. This is the first method. Second thing what we did is we don't have the board available with us. Okay, because we wanted to upload our SRAM object file to the remote lab setup. That's what our idea was. In order to do that, what we moved is we understood the logic of remote lab using the labs LAN setup. That was our second understanding. In the morning, what we did is I showed the first lab with DE10 light, where I connected the board directly with my laptop and then showed the output. In the afternoon, I requested you to download the Cyclone file library because this particular labs LAN setup uses the DE1 SoC board. Please understand, they use the DE1 SoC board. Therefore, it is very critical and important that you should install the Cyclone file library. Okay, because this is a Cyclone 5 FPGA. Now, in this, what we learned is we can perform the compilation in our own laptop. So locally, the Quartus is installed. We did simulation, we did synthesis, we do pin planning, everything you do and perform compilation. Everything we have done in our local system, and we are directly entering into the labs LAN setup in order to upload our SRAM object file. That's what we learned. That was our second lab which we understood and then tried. Then the third one, right? So in this lab, what did we understand? I'll tell you. In the first two labs, it was completely only the pure combinational logic block. Therefore, you don't require the clock pin. But every FPGA will have a clock pin that need to be connected, right? So the clock will have a pin, specific pin, right? So that's what we connected in the third lab, which was our Night Rider. And what is the learning in the Night Rider lab? If you see, by mistake, what is given is the code need to be converted from 50 megahertz into 1 hertz because the board frequency is 50 megahertz. But if you wanted to see the LED to glow, then it should be reduced that into 1 hertz. But in the Verilog code, what is given to you, it is not exactly converting from 50 megahertz to 1 hertz. Therefore, you have to modify your counter size code, what is given, to set to either 23 or 24 in your Verilog code. And then if you rerun and you take that SOF file to the labs LAN setup, you can see that the design works correctly now. Because otherwise, in that case, you can see it will be very fast. Sometimes all the LEDs will glow. We really don't know what is happening. Okay, when you reduce the frequency, then we can see that, okay, it works step by step. That is the idea of the third lab. The first two labs are combo logic. The third lab is a sequential logic, which you can understand. Right, that is what we have seen in the second hands-on lab. The third one, what I wanted to make you understand is, whenever you go to the tools, like for example, if you open any FSM viewer logically, what is the guarantee that the FSM code what we have written is exactly showing the kind of state diagram what we have in the notebook, right? So in order to get that idea, in the earlier demos, we have seen only three viewers. One is called as the RTL viewer. The second one is the technology mapping, which is after synthesis. Other one is after placement and routing. But in this example, we also need to see that what is possible after fitting. That's what we wanted to see. The last option, which is called as the state machine view. That's what I wanted to show you. In this example, what I wanted you to do is you perform the simulation first. Ensure that the test bench works and you can analyze the waveform. And I wanted you to check all the four, like RTL viewer, technology map viewer post mapping, technology map viewer post fitting, and also the state machine. Right. And lastly, what I also introduced you is the remote lab setup, where you don't want to use labs LAN and you don't want to connect the board physically to your laptop sitting in your home. The third one is you can have the FPGA boards hosted in the institution server, and you can get the server username and password and access the board remotely. So that option is also available in our remote lab set. That's what I showed to you, and for that I showed you two demos. Right? If you have any other further questions related to extra learning, please let me know. The PPTs would be converted into PDFs, and then we will put that in the Google Drive. That would be shared. Give us some time after the session. I will do that and put that in the Google Drive. It will be accessible for you tonight. Definitely, we will learn platform designer as a part of this course. Our main aim of is the objective would be probably from Tuesday we will be getting that. Tuesday, Wednesday, Thursday we will be touching upon the platform design.
Dear participants, if you have any queries, you can raise your queries.
Yeah, please. So the objective is that you have to get hands-on with the labs, right? It doesn't mean that we should give multiple labs and then you should get confused. Okay, the idea is like you have to get a hands-on with the basic labs. You should be thorough with what happens in each and every step, and then it is easy for us to go to the next phase. For example, how it is planned is like if you know the basic quarters flow, then we will be getting understanding of timing analysis. Then you will be getting to know how to do a system starting from Monday. Like you will be getting the objective of high level synthesis, you know how to do SOC design, you know how to do AI like that, right? So once we are very comfortable with the block level, then taking that to the system level would be easier. Okay. Yes, we can try that 21.1.0, not a problem. You can try that version, no issues. Any version is fine, but the problem would be only when it is coming to the specific labs, which I will let you know. If there is any problem, then we will try to sort it out separately. The PDF materials are shared in the drive, both the Intel FPGA portfolio as well as the Intel Quartus Prime design software PDF slides. You can go through it, and you also have the lab manual with you, and you also have the lab files, both related to labs land setup, the lab manual, and the lab files. Also, you have the FSM labs. Everything is available with you. You can just have a practice of it.
Thank you, Patwanabham, sir. And thank you all participants. Now we can wind up the session. We will again meet tomorrow morning at 10 a.m. sharp. We will be having our sessions from 10 a.m. till 5 p.m. And for any request, you can check the schedule, as well as all the informations have been shared in the Google Drive, which is shared with you in the registration confirmation mail.
Fine, Vipula. Thank you very much. Thanks all the participants for your patience and listening and then doing the hands-on lab. So, right, it would be better that if you practice all the labs every day so that it will be getting a good idea of how we can explore Intel FPGAs better. Thank you very much. Let's sync up for tomorrow's session.
Thank you, sir.
Thank you.
Participants, we will be disconnecting the meeting in another 2 seconds. আজি complete হল, খালি আছে।